So thank you, everyone. Welcome to the 2021 virtual SEPM Deepwater Research Group Forum. My name is Fabien Laugier. I'm one of the three co-chairs along with Lilian, Navarro, and Emma Morris, who's unable to be here right now, or I think she'll be joining in a bit, we'll see. Yeah, so thank you so much for taking the time. I know how busy typically this point in time the year is. So thanks for taking the time to join in. And today what we're going to be talking about is essentially discussing some future directions of deepwater sedimentology and stratigraphy, looking at both new avenues of where research is going, different topics, but also focusing on different technologies that are being used to address some of the questions we've had for a long time. So it's a pretty packed agenda today, and we'll go through that. But before we start, I'm going to jump to this slide right here, just focusing on, event ethics and policies. I know we're all virtual, right? But let's, ensure that kind of all the interactions that we have, all the discussions, do follow the SEPM codes of conduct. And we really want to make sure we're respectful of all the presenters, all the attendees. So please, again, thank you so much for joining in, and respect the time that everybody's put in to put this on, and all the discussions and questions that we'll go through today. Excuse me, there we go. So to kind of give direction of where we're going to go today, just to make sure we stay on track, we're obviously going to kind of introduce what we're doing, why we're doing it. And then Cassie is about to launch a quick poll. We just want to kind of, get a feel for who's attending, how you heard about this, different things like that. And then we have a pretty excellent list of panelist presenters to start that you can see right here. Then we'll have a quick Q&A, then go for a break, and then we'll start another series of discussions as well. So again, thank you so much for taking some time. And Cassie, how about we launch that poll now? And Lilian, let me know if you kind of wanted to add anything to that. I want to try and make sure we're on track.
No, we are fine.
All right, the first one is, are you an SEPM member? We're going to give you a minute to answer that, so you have time to answer that. And once we get a few of the responses in, we will close this poll out. And if you're not an SEPM member, we are going to send you that link so that you can find out how to become an SEPM member. Okay, we've got a good amount of percentage voted, so we're going to close that poll out. Okay, and we're going to, here's the results.
Excellent. What I see is an opportunity for 43% to become SEPM members.
All right, now we're going to launch our second poll. This one is, what category do you identify yourself with currently? Okay, we have about 90% voted, so we will go ahead and do that. All right, there's the results. Okay, Fabien, that's back to you.
Again, before we begin, thanks for taking the time to fill out that poll too. Just to make sure we're on track, we're going to launch right away. But one of the key things we really want everybody to think about while while all these presentations are going on and in the discussions in the QC, when the kind of Deepwater Research Group is putting together and trying to decide, what the topic of the theme would be, kind of solicited feedback from a lot of individuals, and and kind of got a sense that there was a lot of active new research being done and a lot of new technologies being used to do that research. And we really wanted to, one, focus on that and kind of come together, obviously, as the Deepwater Research Group community to try and showcase some of that work and maybe try and, build on the work that's going to be shown here today, so that we can actually kind of continue to advance the discipline as a whole. So please do keep that in mind as we're going through all these presentations.
Hello, everybody. I'm very glad to be today with you. I would like to start say thank you for organizer to invite me to this forum. I'm quite excited to the discussion that we could have today. So I'm going to speak about the influence of bottom currents in deep marine environments. So can you please pass next? Okay, so I'm very glad because during the last 4 years, we have a consortium with the industry, and probably these 4 years were the most intense and exciting year in my career, where we could have the opportunity to study a lot of areas that you can see in this map, and compare this area for the same topic to understand the influence of bottom current, not only today, but also in the past. So we study all these we have studied directly or indirectly in all these areas, offshore, and also in 3 outcrops in Cyprus, Morocco, a little bit on Angola as well. So next. So this was a consortium funding by Fabien, for several companies that you can see here in the bottom. So as a general introduction, I think we all assume that gravitational processes are key processes in transferring sediment from shallow marine to deep marine settings, But based on all the area that we have studied, next, Fabien, we identify the ubiquitous occurrence of deposits being affected by bottom currents from the upper slope to the abyssal plain. And in all the samples, we have a very interesting interaction between bottom current deposits, gravitational deposits, and hemipelagic or pelagic deposits. Next. Fabien?
I think there's a bit of a lag, apparently.
Okay, thank you. Well, doesn't matter. Well, some of this interaction is desynchronized, so the processes are happening at different time, but some of the interaction are synchronized, so they are happening at the same time. Most of the bottom current deposits are very big deposits, so they are based in scale sometimes, being along the slope, as you can see here in this light blue, or at the foot of the slope, okay? So that is interesting because then thinking in future, that is my main aim today, we have to perhaps review the concept of source to sink, because most of the sediment provided by gravitational processes is at the end on the slope, especially the fine grain particles. Next, Fabien. So in the next slide, I'm going to summarize that from my view, are the key aspects for future. So I'm not going to focus in any area. I try to combine most of the results we got to provide some idea for the discussion later. So I'm going to start with plate tectonic and gateway. So the evolution of gateway, because plate tectonic is really key in controlling the onset and the evolution of most of the large contourated deposits. So we need to clarify in future the signs of contour current activity in the geological record. And it's interesting because most of the big contour deposits are more or less in the same edges. So we need to understand that, and also we need to have better dating with higher resolution to compare these deposits. Next. In terms of long scale deposits, there is a large depositional and erosional feature, and there is a nice link between this feature and the physiographic domains along the continental margin. So I really want to say that depending on in which setting you are, we have a similar type of contours. And we have this large deposit, but also we have a smaller deposit within the largest one. So that means that we have different processes acting perhaps at different time and also at different scales. And most of these deposits have a common evolution, starting, as you can see in this example, from taural deposit to mounded deposit being later buried and fossilized by other kind of deposits. So we need to understand better what is the long-term factor controlling this common evolution. And also, in more detail, there are some vertical and lateral variation within the deposits, probably because lateral changes in the water masses, in the behavior of the water masses. Next. And related to that, there is a nice cyclicity in this kind of chondritic deposits. In a shorter scale, it's mainly controlled by climatic variation, for example, in the scale of Milankovitch, but also in a longer scale, but not very long, tectonic fluctuation or tectonic pulls are really very important in controlling the stacking pattern of these deposits. So some authors have identified variation in the scale of 2 to 2.5 million of years, and also 0.9 to 0.8 million of years, and a very interesting variation around 0.4 million of years in controlling the stacking pattern of the deposit. So there is a strong link as well with tectonic, not only with climatic variations. And some drifts are not included in the present classification. So in future, perhaps we need to review this classification. Next. And also, we try to accept that progradational bodies are mainly in shallow marine settings, but also in the deep marine setting, we can identify very large sedimentary or lateral sedimentary migration of deep systems related to contours. Next. Of this example from Argentine, where you can see this body progressing or migrating upslope in a large scale. So this kind of deposits are very common in the deep setting. And in some cases, not this example, but in other example, they mimic clinophore or they mimic clinothems. So we have to understand these progressional bodies or lateral migration bodies in future more. Next. In the outcrops, it's also possible to identify the deposit, and now we have more evidence and more criteria to identify them. But in the last year, it's amazing how different groups are doing very detailed work. And it's very important, the geological setting and the paleogeographic setting, to understand why we have contourites in these paleomargins, but using next more detailed sedimentological analysis, it's possible to identify the depot-center distribution and decode the geometry of the sedimentary bodies. And there are some groups at the moment in Germany and several groups in the States working in this kind of analysis. And probably in coming year, we're going to see very good example of contour system, even in a large scale, using outcrops. So we need to investigate this more in future. Next. In terms of processes, next, thermal circulation is the framework, and global circulation the framework, not only today, also in the past. But also we know that there are other secondary processes next affecting to the geostrophic circulation. So the ocean is quite complex, and there is a interrelation of many processes at once, next, that are controlling deep marine sedimentation. Next. And these secondary processes modulate the velocity and the direction of the local bottom currents. And most of these processes are intermittent. And this is something as well to check in future, that we assume that control processes are permanent or semi-permanent, but in fact, most of these processes are really intermittent in a longer scale compared to gravitational one, but also intermittent. Next. So we need to understand better these processes. We need to visualize these processes. And one way to do that in future is to analyze more seismic profile in the water column. Next. But especially, we need to see, or we need to understand the interaction of this process against the seafloor that we call the boundary layer. Next. So the boundary layer is really the great unknown in this topic. We don't really know what is going on above the seafloor, especially in the first 20 to 25 meters above the seafloor. And we need to understand that better to really go further in this topic. Next. And you can see here one example from the Gulf of Cadiz, where you can see a distribution of phases because the local behavior of the current, and then laterally their expression in a core, you know. So we need to go in this detail to understand better the phases and phases association related to contours and mixed system. Next. And briefly, in terms of sedimentary phases, we have, it's a simplification, I know, three kind of phases. The classic contours, they are the muddy contours, the sandy contours, and also that we call the reworker turbidite. So turbidite that have been affected by the bottom currents. Next, you can see here on the right one example. We have this model at the moment, the gradational sequence, that is working mainly on drift, but also next. We have a problem with the gradational sequences because normally they are very bioturbated. So we cannot really see the preliminary sedimentary structure because of bioturbation. But we saw that in some areas, like polar margins, we have less bioturbation. So perhaps we need to explore more examples in these settings with contours to really understand the detail of these gradational sequences. Next. And people started to develop new models where there are phases and phases association related to the different suit environments, from the erosional element of the system to the flank of this erosional element, for example, continuity channel, to the adjacent drift. So the model become more complex than we saw. Next. And something that we have identified in all the sample is that in all the different phases, we have a banding or a bedding of 2 to 5 centimeters, like this example from Cyprus. And that means that this long term from weaker to stronger current to weaker current is probably more complex as well as we saw. So we need to explore this little variation in future to understand more the behavior of the currents and also the associated phases. Next. There are big explosions at the moment about mixed depositional systems that represent the interaction of gravitational processes with bottom current processes. They are very frequent today and also in the past. And we know and remember when turbidite processes are dominant or when bottom current are dominant in this interaction. But there are also some intermediate situations that we need to explore in future. As in the continuity system, this mixed system have secondary feature. So there are some similarities in some way, and also they also have a common evolution, as I said, for continuity feature. But we need more examples. We need to understand this mixed system more in future to propose new conceptual model. Next. And as in the continuity system, the distribution of phases is not that simple. So it's different the phases related to the submarine canyon, to the flank of the submarine canyon, to the drift that is perpendicular to the margin, not parallel to the margin, as in the continuity system. So we need to have new example, because so far we have two, to understand this variety of phases in mixed system that is not the same compared to continuity system. Something as well for investigating future. Next. So finally, and this is my last slide, what is my final comments about the topic for the discussion today? So it's really necessary to monitoring and quantify these sedimentary processes with the help of numerical models. So we need to really measure this process in the mother ocean. And we need to connect the hydrodynamic to processes and then to the deposits. And we also need to collect data series from a long period to understand the behavior of the bottom currents. Next. So this is, from my view, the only way to really have a new revolution in the topic and to propose new models. So all the models we have are very theoretical, but they have not seen really in nature. We need to go to nature. We need to measure the processes to understand the products. And this is something probably a challenge for present future. Next. And also, we need to understand more this interaction of processes, not only to identify the products, the deposit, but also to quantify and to date when they are happening. Because again, we have intermittent processes related to contourides and bottom current circulation, and gravitational processes, as you know, are also intermittent. So we need to know the dating or the when they are happening and when they are really interacting each other. And the last one, Fabien. Next one. So I have finished it. So thank you for your attention. I'm sorry for do the presentation in this way. We have problem in sharing the presentation before. Just to let you know that next year we have 3 international meetings, one in Lisbon in May, another one in Edinburgh, the 4 Deepwater Circulation Conference, and the last one by November in the Geological Society. And that's all. Thank you for your attention, and I will be happy to answer any question later. And thank you, Fabien.
No problem. Sorry, I wasn't able to turn off my camera. It didn't give me the option. So excellent presentation there. As you know, as I forgot to mention at the beginning, we're going to be holding questions until after the first kind of series of talks that we do have. So write down your questions that you do want to ask, or add them in the chat, and we'll kind of get to them towards the end. But again, Javier, excellent presentation there on that topic. So.
Hi, my name is Celeste Cunningham, and I'm doing my PhD at the University of Ottawa. Today, I'll be talking about my project on carbon deposition and preservation in ancient deep-sea levee sediments. The rock size study belonged to the Windmill Superl group, which is a 6 to 9 kilometer thick succession of mostly marine rocks deposited on a passive margin after the breakup of Rodinia in the mid to late Neo-Proterozoic. My research group, led by Bill Arnott, studies the deep marine slope deposits of the Windmill Superl group, and my doctorate project looks specifically at the levee deposits associated with slope channels. My fieldwork is conducted at the Castle Creek study site in BC, Canada, where levee deposits are exceptionally well exposed due to glacial polishing. This allows for detailed observations to be made at a wide range of scales. Additionally, samples taken from the field were examined using both optical petrography and scanning electron microscopy, as well as analyzed for TOC and carbon isotopes. 2 organic-rich facies have been recognized at this site, organic-rich sandstone and organic-rich mudstone. The TOC in these facies can be as high as 15% once they've been adjusted for the effects of green schist metamorphism, which is estimated to have resulted in the loss of 50 to 80% of the original content. Organic-rich mudstones are black and extremely fissile, and consist mostly of clay with lessile amounts of silt. They also contain abundant rhomboidal pyrite, as can be seen in the photo. Organic-rich sandstone beds consist of alternating bands of black, mud-rich sandstone and orange, highly cemented sandstone. Soft sediment deformation, such as flame and lode structures, are quite common in these bands. Organic-rich sandstone is the more common of the 2 facies and constitutes most of the organic-rich beds at Castle Creek. The OM can be grouped into 3 types: discrete silt to sand-sized carbon grains, sand-sized organomineralic aggregates, and nanometer to micrometer scale totons around clay grains. Types 1 and 2 are interpreted to be detrital grains, soils from disaggregated bacterial mats that grew on the continental shelf before becoming remobilized downslope. However, these two types are relatively uncommon. Type 3 constitutes about 90% of the OM, and it houses thin, flat totons around and in between clay grains. The clay grains in the black, mud-rich sandstone bands, like the clay grains that comprise the OM-rich mudstones, are associated with this type. This OM is interpreted to have originated as freely suspended micro and nanoscale organic compounds and EPS from the upper water column over the continental shelf. These then became physically and/or chemically adsorbed onto the surface of clay grains and were subsequently resedimented downslope. So why is the OM concentrated in levees? Although primary productivity is highest on the shelf, OM can get transported downslope by sediment gravity flows. When this happens, much of it is adsorbed onto clay grains, as we've seen, and as such is concentrated higher up in the flow and ultimately ends up over spill in the channel and being deposited on the levees. The high sedimentation rates in this environment, coupled with the additional protection by chemical adsorption, prevent its destruction by oxidation or respiration, and this effectively sequesters huge amounts of carbon in the sediment and acts as a sink for atmospheric CO2. Significantly, this preservation can occur without any special conditions, such as bottom water anoxic events in the ocean. This study has shown that considerable amounts of carbon can be buried in deep sea levee systems. However, carbon burial in the Neoproterozoic is not necessarily representative of modern systems. In the Neoproterozoic, terrestrial plants had not yet evolved, and so the OM being transported downslope was only marine and as such was dominated by these organic compounds bound to clay grains. However, recent studies of modern systems have found that terrestrial OM constitutes a significant portion of the OM found in levees and in other deep sea sediments, and that most of this OM actually occurs as grains in sands rather than in muds. This suggests that although carbon burial in levees was significant in the Neoproterozoic, it is even more so now. For example, recent studies have estimated that approximately 3.5 million tons of new organic carbon are delivered annually to the Bendel fan system. Future studies should focus on examining the relative input of terrestrial and marine OM and the mechanisms and efficiency with which each are preserved throughout geologic history in order to better evaluate past and present global carbon fluxes. Thank you for your time.
So, hello everybody from King Fahd University, Saudi Arabia. Thanks to SEPM Deepwater Group for the invitation to speak to you today. Before starting, I would like to acknowledge these people and these organizations for their help to carry out this research, as well as share these research results with you. Let's get started. So, as Celeste talked about, give a bit of context. So, sediment gravity flows are the largest sediment transport agents on Earth. Yet these are the least understood ones. So they could carry significant amount of organic carbon from the shelf areas to these different deep sea environments. Studies, observation from the modern fan systems such as Congo and Bengal sort of suggest that these different fan environments could be pretty efficient in sequestering large quantities of organic carbon, as you can see in the chart on the top left. And the amount of carbon that is buried in this system is sufficient to impact climate over the geological time scales. Conventionally, mudstone in these settings have been sort of considered as a sink, but emerging evidence suggests that more sand-rich facies such as TB and TD divisions and turbidites can also store sufficient amount of organic material. Two really nice examples from the Bengal fan, from Lee et al. And from the Butte Inlet in British Columbia from Sophie Hague, where these TB and TD divisions are sort of pretty efficient in storing organic material. But deep water systems are composed of many other flow deposits, like the ones that exhibit mixed sort of behavior or hybrid character. And in some sort of in some settings, they make a significant part of that sort of deep marine settings, such as distal lobes. So understanding how organic carbon is sort of distributed and what sort of impact of these burial processes can be on the organic matter is important to understand. So for this, so how these hybrid flow works is basically a sand-bearing flow is acquiring a lot of mud and mud clast, and this is sort of forcing distal flow transformation, resulting in this deposition of these complex tier deposits that we call hybrid event beds. So this on the right, we can see this idealized hybrid event bed model produced by Houghton et al., where we have this, it says 5 parts to it. We have the basal H1 divisions, where we have, which is sort of a cleaner sand deposited by turbidity currents. We have H2 divisions, which is sort of composed of alternating bands of darker sand and paler sort of layers deposited by transitional flow. We have this sort of muddy sandstone and sandy mud divisions in place by blank debris flows. We have this H4 division, which is sort of structure sand, a thin component of the flow deposited by low density turbidity currents. And then we have this H5 divisions, the muds that are deposited from the suspension fallout. Looking at these sort of structure of hybrid event beds, what we can see is that it's a product of more than one flow process, but how these different processes impact the distribution, abundance, and burial efficiency of organic carbon. To address this, we have studied Ross Sandstone Formation, which is an ancient tropical deep sea fan system exposed in the cliffs around the Loop Head and County Clare, west of Ireland. The reason to choose the Ross Formation was that it has been drilled recently with the help of Equinor, and a lot of fresh core material is available for the analysis. Secondly, it has been logged, so the cores have been logged, and a lot of different types of hybrid event beds formed by different processes have been reported. So it's kind of a really test sort of initial material to test how carbon can be buried by these different flow processes. So the bed inventory compiled on the basis of the core is that Ross is composed of turbidites and 9 different types of hybrid event beds. Previously, Ross was thought that it is only composed of turbidites, but the core shows that it is composed of other deposit types as well. And the hybrid event beds form about 1/3, so about 30% of this bed mix. What we did is we sort of, these hybrid event beds occur at a different stratigraphic interval. So what we did, and they can be grouped into 3 different facies tracks. So at the basal part of the Ross, we can have this basin flow sheet system where these thick, coarser grained sort of hybrid event beds have been deposited in these basin floor sheet sort of systems outboard of this main fan system. And the lower Ross, we have these more muddier sort of hybrid event beds inferred to be deposited in the outer fan sort of settings. And then in the mid to upper Ross, we have those thinner hybrid event beds deposited in more sort of mid fan distributed channel lobe system. So we have analyzed these different bed types from different environments using petrography, organic geochemistry, and inorganic geochemistry as well. And what we can see is that H1 divisions are relatively organic lean in this hybrid event bed types, and most of the organic carbon is like efficiently fractionated towards and the H3 divisions. So the carbon isotope data shows that organic matter is mostly of terrestrial nature. Another bed in the similar sort of settings with H1 division absent, but a thicker H3 division. And what we can see is that sort of organic carbon content in H3 division is sort of increasing towards the bed tops, towards the top of H3 division. Again, the similar sort of organic carbon terrestrial. Further up in the system, where we have these thinner hybrid event beds with thinner H1 division and more sort of expanded mudstone caps, what we can see here is that the trend is more or less similar, very thin H1 divisions, and then sort of organic carbon content increased towards the top. And organic matter remains the same, so it's terrestrial. Another hybrid bed from mid-fin sort of settings, and what we can see here, again, more or less the similar type of trend. H1, organic clean relatively. H3, organic carbon content is relatively higher. It's increasing towards top of the H3. Oh, sorry. So it's just increasing towards top of the H3. And sort of one of the interesting thing in this hybrid bed we can see is that organic carbon organic carbon content is more in H3 division than the cogenetic H5 division. And this trend has been observed in many beds. So sort of summarizing all of those bed data from all of those bed types, what we can see is that H3 division H3 division store more organic carbon than their cogenetic H5 divisions. And we believe that this is due to because H3 divisions were rapidly deposited due to en masse freezing compared to the H5 divisions, which were slowly settling from the suspension. This is further verified. So what we have seen, one of the interesting thing in these hybrid bed H3 divisions is that a lot of that organic carbon is sort of encapsulated within these clay flocks or aggregates. So perhaps when flow began to flocculate, it sort of really dumped a lot of organic carbon with it. Sort of summarizing all of those results into these two into this cartoon is that in turbulent flow, the deposition is incremental, so grain by grain deposition, and so organic carbon is mostly accumulated towards top TD or TE divisions, which are, and these divisions are prone to resuspension, reworking, and sort of to oxidation. While compared to these turbulent flows, hybrid event beds lock their organic carbon content into relatively lower tiers, such as you can see the H3 and H3B divisions. So we think that this sort of locking and this mechanism offers more protection and compared to the turbidites. So in conclusion, hybrid event beds can dominate distal lobe stratigraphy, but they are still underrepresented. Sink, clay-driven flow transformation provide an efficient mechanism for rapid burial. Encapsulation of organic carbon within clay flocks may prevent carbon degradation and promotes enhanced preservation. And one of the most important things is that proportion of the hybrid beds should be considered while we estimate the carbon burial budget in the deep sea fan in the future. So with that, I thank you.
Hello, everyone, and thank you very much for the invitation. And today I will talk about the global plastic pollution crisis and the role of deepwater sedimentology. I believe and also hope that we can all agree that we are facing a global plastic pollution crisis. Since the 1950s, we produce millions of tons of plastic each year. In 2017 alone, 438 million tons of plastic were produced. And the prediction is that there will be an exponential increase of plastic production over the coming decades. Plastic is an amazing material with unique material properties in various areas of application. But unfortunately, quite a lot of plastic is used for single-use throwaway products. 35%, for example, is used for packaging. And this is no surprise. Consumers have been educated over decades to view plastics as easy-to-use throwaway products. And all this resulted in the accumulation of 9,200 million tons of plastic in total. 2/3 of the produced plastics, 5,300 million tons, is now turned into plastic waste. It's been estimated that 39 million tons of plastic entered the environment only in 2020. This graph here shows the estimated plastic pollution in million tons per year over the coming decades under different scenarios. And if we continue with business as usual, this is indicated with this red line here, the annual plastic pollution will increase to 80 million tons per year by 2040. Even with immediate and concerted action, so if we keep pollution at a constant level, or if we even decrease it, we may still accumulate 710 million tons of plastic waste in the environment by 2040. And this is very concerning because there's growing evidence for ecological harm from plastics. In the environment, plastics typically break down into smaller pieces, which increases the overall surface area and potentially benefit the release of toxins. And this may result in a peak of toxic release in the future. And as a result, there might be widespread ecological risk coming from plastics in the next century. And again, this is hugely concerning because plastics are widely dispersed in the natural environment. Plastic is present in the oceans. We can find it in deserts. And microplastic fibers were even found in snow near the peak of Mount Everest. But for now, I would like to focus on plastics in the marine environment. Rivers are likely to be the main pathway for plastics into the oceans. However, there's also plastic input coming from shorelines or from ocean transport. It's been estimated that roughly 10 million tons, give or take, of plastic enter the oceans each year. We now estimate that more than 5 trillion pieces of plastics are afloat in the world's ocean. And these floating plastics accumulate in the subtropical gyres, forming the 5 garbage patches. This seems like a lot of plastic, but apparently it only accounts for 250,000 tons. Remember that roughly 10 million tons of plastics enter the ocean each year, so only a fraction of the ocean plastic is afloat. If you crunch these numbers, you will find out that 99% of the ocean's plastics are missing. We don't know where it is. It's been suggested that most of the missing plastics are stored in deep water sediments. And this leads me to the second part of my presentation, where I want to talk about plastics and deep water sedimentology. And I would like to address 2 points here. First, can deep water sedimentology contribute to solve the global plastic pollution crisis? And second, could we use plastics in the study of deep water sediments? So basically, could plastics help to better understand sedimentary processes in the deep sea? I think it is unlikely that deep water sedimentology will help to prevent plastic pollution. We don't look at the source of plastic pollution, we look at the sink of all the plastics. And what we can do is we can identify and specify the scale and impacts of deep marine plastic pollution. So let's see what we know about deep marine plastic pollution. There's only a very limited number of studies available looking at plastics in the deep sea. But from the studies we have, we know that there are microplastics on the seabed. It is still very difficult to estimate microplastic concentrations across different marine environments. This early paper by Fabien et al. Found highest concentrations to be in submarine canyons, with concentrations of up to 1,000 plastic pieces per square kilometer. However, more recent research actually indicates that these numbers might be much higher, more in the order of tens of thousands of pieces per square kilometer. And in addition to these microplastics which are sitting on the seabed, we can find microplastics in the sediments. So microplastics are plastic particles or fibers which are less than 5 millimeters in size. Typical concentrations of microplastics found in deep marine sediments varies between 0 to 4,500 particles per kilogram of sediment. Also for microplastics, it is difficult to estimate the magnitude of pollution across different marine environments. Again, mainly due to the lack of studies. However, initial studies indicate that concentrations are highest in submarine canyons, in trenches, and in contourite drift deposits. In summary, deep marine sediments may likely present a terminal sink for the ocean plastics. However, there's still only limited information available, and we have a quite blurry picture on seafloor plastic distribution. Highest concentrations appear to be in submarine canyons and channels, in ocean trenches, and in drift deposits. Now to come back to my first point, what can future deepwater sedimentology deliver to solve the plastic problem? Well, I think we could help to understand transport patterns and the dispersal of plastics across the seafloor. This would also mean to estimate seafloor plastic budgets and to find out how much of the missing plastic actually made it to the seafloor. Further, this includes to identify plastic accumulation hotspots and associated ecological risks. And finally, find out about the fate of deep marine plastics. Are they buried in sediments? How do they deteriorate on the seafloor? Basically the question, what happens with all this litter over the coming decades? And how quickly could polluted environments recover? And this could help to develop effective strategies to prevent plastic from reaching the deep sea. We could answer the question, what are typical plastic concentrations in certain marine environments, and would it make sense to define specific upper limit values? This could guide legislation and may also guide decisions on which areas we want to declare as marine protected areas. In the last part of my presentation, I would like to share some ideas with you how we could use plastics in the study of deepwater sediments. Could we use plastics or polymers as stratigraphic marker? The first plastic was synthesized in 1907 by Leo Baekeland. He called his invention bakelit, a plastic polymer which you might know from old telephones. Since then, several other polymers have been developed and produced. And the basic idea now is that the abundance or absence of specific polymers in the sediment could provide the maximum deposition age. Here, the maximum deposition ages of floodplain sediments were determined by different plastic polymers. The lowermost sediments were free-form plastics, suggesting an age older than the 1950s. In the overlying sediments, however, different polymer types were present, and the maximum deposition age could be associated with the development and production of these polymers. This method might also be useful to determine the maximum deposition age of deepwater sediments. Sadly, though, it only works because of the wide dispersal of plastics in the environment. Another idea is to use plastics as a unique tracer with the opportunity to learn more about deep marine sediment transport and pathways. A nice example about the main concept of this idea is the story about the friendly floaties. In 1992, a cargo ship in the North Pacific lost a container with more than 28,000 rubber ducks, which started a years-long journey across the world's oceans. Eventually, and sometimes after years at sea, the ducks washed up on coasts, and the distribution and timing of the reappearance of the ducks provided a way to monitor ocean currents. Could similar approaches be used in future deep marine sedimentology? Could we potentially link specific plastic items or polymers to a certain source to understand source-to-sink pathways? Different plastics have different hydrodynamic behavior due to their variations in shape and density. The abundance and distribution of certain types of plastics could provide information on sediment transport processes. Song and Peng, for example, use microplastic litter piles to reconstruct flow pathways in a submarine canyon. Similar, can the study of the transport and deposition of different plastics by sediment flows also provide information about fundamental physics of these flows? I'm afraid that this is all I can squeeze into 10 minutes. Nevertheless, I hope my presentation provided some food for thoughts and that you enjoyed it. Thank you very much for your attention, and I'm looking forward to the discussion.
I think so. One of the key things, while people figure out, some of the questions they might want to ask, I think one of the things that's very exciting to see across all the presentations that we've already seen, and one of the reasons we wanted to have this kind of future direction topic, is that there's a lot of work on, there's clearly a lot of work on trying to improve or develop new understandings of deep sea processes and develop the depositional models that might be associated with those. One of the kind of benefits of obviously having those, and in conjunction with all the work that Celeste and Arif are doing, as well as Florian, is to understand, well, key things like organic carbon, micropollutants, where are these things going? If we have incorrect depositional models about where these things are occurring, the lateral extent, the spatial extent of how big these deposits that they're associated with could be, we might be having completely skewed models for that carbon budgeting and that burial of pollutants. And so I think one thing that this has really shown, and that we really wanted to communicate, in addition to what the presenters have just done, is that there's actually a lot of active questions. And I think there's a lot of active interest right now, as we see throughout the community, on exactly these topics. And I see that there's a couple questions that just appeared in the chat on my end. I can't click any of them. Lilian, I didn't know if you were able to click on them.
Yes, I can see some. We have one of the first question is Brian Romans from the Virginia Tech, and he's saying, Javier, thanks for sharing. I agree with you that a critical next step is to link actual measurements, the bottom currents velocity, with the deposit character, To do this will require a significant investment, and he referred to the Hubble project in Nova Scotia, and Margin, and it took place in the late 70s and early 80s. That was funded by the US Navy, but they aren't as interested in this expensive deep ocean field work as much these days. So where does our community go to seek the necessary funding to do this work? With whom should we sedimentologists be developing big proposals with? Would you love to hear your thoughts? So this question is for you, Javier.
Okay, well, very good question. Yeah, I know that project, and it was a pioneer project for understanding many deep marine processes. Well, the only way is to try to have international projects to collaborate more between us, you know, and this is probably the only way. I know there is a couple of groups working in this topic, mainly to understand the benthic boundary layer and the processes above the sea floor. Probably in coming year we will see more and more, you know, paper about that. But this is the only way. I do agree with your comment. The only way. It's quite expensive, but it's the only way. I mean, you have so many theoretical models that they are really working, and it's because they are based on the facets from the ancient record or from the ancient record, but we don't really know the processes behind. So that's the challenges for future.
There is a comment from Ole Martisen, and it was just to say hi and to Arif, and he said just very nice, and he unfortunately he has to leave. And he was the same with Bill Arnott, and he has to teach, and he mentioned it, and he said that he likes the first two talks, but he has to go. Sorry. We have a question from Marco Fenesso to Arif, and he is Arif. Thank you for your excellent talk. I just wonder why in your penultimate slide you associate HEVs as a result of the pure laminar flows and not as in part of the evolution of the turbidity flows in training mud, or rapidly decelerating and collapsing as they are commonly interpreted, as suggested by your introduction schemes.
Thanks, Marco. Lilian, for some reason, I couldn't understand the question fully. Could you please repeat it?
Yeah, so he just wondered, and in your one of your last, the penultimate slide.
Okay.
The associated HEVs, it looks like he's a result of the laminar flows.
Mm-hmm.
And he's wondered, and it doesn't, it looks different from your introductory slides.
Okay, well, perhaps I would, I don't know, Marco, if I understand your question correctly. I'm really sorry about that. Why not write to me, and we can take a discussion from there, if it's okay. You know, because
Yes.
what I understood is I have divided the laminar flow divisions like H3 into two parts, you know, based on our XRF work, if I understand it correctly. Yeah, but sort of we need to simplify the things, as Horton model is already, you know, widely understood. So sort of linking up with it, if I understand it correctly. Otherwise, I'm really sorry. Could you please get in touch with through the email? Yeah, please.
So yeah, so the sorry, Arif, I'm going to go back again. It's just, and he's wondered, and in the, you know, at the beginning you showed, and these HEVs were associated with the evolution of the turbidity float. You have some processes like entraining of the mud and the accelerating and collapsing of the flows. Then in the last slide, it was something showing more like as a result of the laminar flow. So
the cartoon was just, you know, to simplify and to compare the fractionation of organic carbon into the parts of the hybrid beds. Yeah, and hybrid beds can lock the organic carbon content in slightly lower tiers, while turbidites can lock it up into the upper tiers where they are prone to, So it was just a simple sort of comparison. Yeah, but perhaps there is scope to discuss, so we can chat through email if it's okay.
Okay, wonderful. So we have a question that is for Celeste and Arif, and is Kate Gilles, and she is asking, how and when does the carbon becomes attached to the clays? So is whether it's on the shells and then it's transported with the clays, or during the deposition has clays and suspending has organic matter flocculated together?
I think it began when sort of clays began to, if organic matter is completely dispersed in the column, and when clays began to flocculate, there is organic carbon, so it may get attached to it. So it could be just at the onset of flocculation process. Definitely, some of the organic carbon can be sort of transported with this mud class, which is already incorporated, which is part of the mud sort of class structure. So I think it's during the onset of flocculation.
I would agree with that as well, and I think yeah, this would begin on the shelf, and as these flows travel down slopes, they can also erode the seafloor out and re-entrain both clay and any pre-deposited organic matter that can then have the chance to become flocculated again with all the clays in the flow.
So we have one question from Jacob Bass, and he is specifically directing it to Arif. You showed a contrasting vertical distribution of the TOC in the turbidites and in the HEBs. Can you say more about the horizontal distribution of the TOC in the deposits of these different flow types?
Hi, Echo. Thanks for the question. At this stage, perhaps no, we haven't sort of studied it. Yeah, but this is something perhaps we need to do in the future. Yeah.
Okay, this is super interesting. So there is still a lot of work to do. We have a question for, sorry if I mispronounce your name, Surtri Reka Sahu, and it's, hi all. My question is for Dr. Paul. And so can you emphasize on the source of the marine plastic pollution? Thanks and regards from Dr. Srutri Reka Sahu, assistant professor for is in the Saudi Arabia University.
Yeah, hello. Can you hear me okay?
Yes.
Yeah, okay, cool. Yeah, thanks for that question. And so import sources are basically rivers, shorelines, also fishing, but it all comes down basically to mismanaged plastic waste. So it's just that people throw away their waste into the river, or there is no waste system in place, or also that rich countries simply export their plastic waste to other countries to get rid of the problem. So I think the main source, you could say, it is mismanagement of plastic waste, as a mismanagement.
Okay, sorry, I have to make a small correction regarding to Sutri. He or she is from the Fakir Mohan University in Balashore, Odisha, India. So I thought that it was a different place. We have a question for Fabien, and it's a Brando Prater, and he is should or could this community assemble and share contour drift calibration database?
Oh, that's interesting. I mean, I think that might be more, a kind of a question to actually, in a way, most of the presenters. I think there's a lot of active work being done on contourite drifts, right? There's a lot of interesting shallow data, modern data that can maybe be used to actually help kind of build these. And I think with the points that were made today, just understanding the key drivers behind some of those processes and then the deposits they create, that could actually potentially be a very valuable thing for the community to have, is a database on those large scale deposits that are potentially so responsive at a faster rate to some of the processes that we're seeing. They could also be used, you know, along the lines of what Florian and Celeste and Arifa have been talking about today. That might actually help us start developing more robust depositional models, because those could be some pretty big storage tanks for organic carbon or microplastics. So I think that'd be a valuable thing to discuss, and kind of in connecting that to just some of the larger, I guess, goals, you know, as the scientific community in general moves towards more open source data, open source databases, and being able to leverage, you know, more analytical approaches. We need data. We need data that's centralized, and we need data that's accessible and can be something analyzed. So I think that moves along with where the scientific community is going in general. I don't know if anybody else, any of the presenters or Lilian or Emma have anything to add to that. I can ramble about that for a while, but I'll spare y'all that.
Well, I think this is why we are doing this forum. We want people to start thinking about it's necessary that we need to start, you know, putting together a lot of the information that we are generating. And our future is going to depend on that. So there is a lot to do, and yeah, it will be fantastic. We can create that kind of database. I'm going to continue with the questions. We have two questions for Celeste, and it's from Peter Houghton. And first, he congratulates you for the talk, and the questions are: how do you correct the organic carbon content for the green schist phases metamorphism that you have in the rocks that you work? And the second question is, what about the distribution of the Precambrian organic matter? The deep sea floor may have been covered by microbial mats in the accent of grazers.
Hi, Dr. Houghton. Thanks for the questions. Both of them are great. So to answer the first one, several previous studies have looked at the effect that the metamorphism would have had on the organic content, and they've estimated that about 50 to 80% of the original content would have been lost based on the temperatures and the level of metamorphism that these rocks have experienced. So the numbers that I provide typically fall into a range based on that assumption that we've lost 50 to 80% of what initially would have been deposited. And as for the second question, I think that's a great point, and it's still something that I'm looking into. The exact soils of this and the types it may have been is a really interesting point, because as you mentioned, the distribution and the types may have been quite different in the Neoproterozoic than what they are today. So I can't provide a definitive answer at this point, but that is a really great question, and something that I'm definitely looking into.
Nice. So we have a question from Michael Mayal, and it's for Javier. You mentioned that some of the deepwater currents are more permanent and others are more periodic. Are there differences in the structures or the bed forms associated with these different type of flows?
Yeah, that's a very good question as well. Yeah, I think so. Yeah, and you can see this intermittent behavior on the sediment through emission through phase or reworking or condensation deposits, you know. Yeah, but this is really a surprise for us when we compare some of the study areas that they have this evidence of the intermittent in the bottom current at different scale. But the problem that we have at the moment is to date, especially the smaller variation in the behavior of the current. So we don't really know when this change is happening. We have some ideas that could be millennium or centennial scale, but we don't really have too much dating to really confirm the duration of the processes.
Wow, this is interesting. Now we have a question, and it's for Florian, and it was made by Ramon Lopez. What about using debris elements in ancient outcrops like plant remains to compare with the plastic particles in modern sediment? Could some plants remain have similar bulk density as the plastic particles, so to be able to compare them? If so, could this be used in ancient outcrops so they predict where the plastic particles are being deposited today?
That's a quite interesting idea, and I think in theory we could do this. We need to understand how these organic materials or these organic debris and also plastics are transported by different processes, by different flows. So if there are hydraulic equivalent or not, if a leaf is transported in the same way like a plastic film, or a piece of a tree like a plastic fragment, I think with experiments we could answer some of these questions. And there are already, I saw already papers, they described plastics in beach deposits, so really layers of different types of plastics which are incorporated in the stratigraphy. So there's already it goes already the other way, so we can already find plastics in deposits and learn from the processes there.
Wonderful. So we have one, Marco say that is fine, Aris, and he's going to contact you, or you can write to him and you can chat up more about this. Now we're going with the question from Tim Dencom, and he is asking to Celeste and Arif. Both showed that the organic matter can be concentrated in the lobes and the levee phases. Could the microplastics travel with non-anthropogenic matter and be much more concentrated there, as at the lobes or levees, than in the channels and other places listed by Florian, which are low sedimentation rate or have little net preservation? I think this question is actually for Celeste, Arif, and Florian at the same time. So I think let's go start with the first part. It's just like you guys showed that either is in the slope or is in the levee phases, you find the organic matter concentrated.
It's less sure it's in the levees, and I showed it's in the lobes and distal lobes where these hybrid event beds tend to dominate. So, but there could be in the proximal sections as well if the organic material is sort of, it's a high density material and could transport as a bed load and sort of can be deposited in relatively proximal settings as well as in the turbidites, you know. So so it can be in the lobes and levees are sort of considered as the hotspots, you know, and data from the modern fan systems also shows this, you know.
Yeah, I think it would depend a lot on the size and type of the plastics. If they are very lightweight and low density, then they could be concentrated as well with clays in some of these distal lobes and levees. But you know, as it's been said, if they are high density, big pieces, then they would probably travel more also in the channels and be deposited with other sandy high density grains.
I think Sophie in her paper showed that quite a lot of organics are deposited in the sand, actually in the axis of the channel, which was quite surprising. So I'm not so sure if all of the materials would end up in the distal part just because they are lightweight. And also in my experiments, I found that quite a lot of fibers were deposited in the sediments. Despite, I mean, if you think about the microplastic fiber, it's quite easy to keep in suspension, and this, even though we found a lot in the deposits. So I think this is quite an open question where we can assume that they are in the distal deposits or in the levees, but we need to check that, I think.
Yeah, this is interesting.
When we talk about the plastics, so.
Of course. Yes, but it's interesting that we are trying to, maybe we are trying to use the same processes for different type of particles and they behave in a different way. Okay,
Yeah,
so sorry.
I just mean physics are the same, so it should work.
Yes.
Fair point.
Yes, it's true. Okay, so the next question is going to be Lorna Strachan, and it's thank you very much for all the speakers. It really is interesting to see the shift in the research focus to using the deep marine processes and deposits to understand the environmental impact on humans. And this is a significant shift from just the hydrocarbon focused research. It will be interesting to find out if the researchers are now securing funding from their work from different stakeholders. I don't know who wants to answer that question. So thank you, Jody. So make a comment about that. We would like to see the panelists video. There is a question from Yvonne Speciala, and her question is: thanks everybody for the excellent talks. And the question is for Aris. Will you still be able to determine what the organic matter was sequestered in the hybrid beds? The rationale for my question is about the evaluating the amount of freshly buried organic matter and the potential of recycled organic carbon. Can stem from the eroded sedimentary rocks in the hinterland, and this is important for the carbon burial fluxes.
I think so. Thanks, Yvonne. There's a bit of disruption for some reason, but I think so. Sophie Haig, she did a really nice job, and she sort of showed where the younger sort of organic material can end up and where this older sort of from the older rocks can be recycled, and which part of the turbidite deposits. So there is a paper, I think so. I don't think I can add any further to that because all of my organic matter was sort of old sort of organic matter. So all we were trying to do is to understand it from really process sort of perspective where it's ending up. So it wasn't a different type of organic matter. Otherwise, I would have been confident to comment on that. Yeah.
Okay, so I'm going to have, there are 3 more questions. One of them is from Guillermo Bossetti from the University of Strasbourg, and is for Florian. Do you have any idea whether there has been more detailed studies focusing on the amount of microplastic found in submarine channels and fans related to the highly populated regions versus the developed or underdeveloped countries? For example, offshore of the Pearl Rivers in the South China Sea, where they have the highest populated place on Earth?
Well, there are not many studies on deep sea microplastics at all. There is, in terms of channels or canyon systems, there are studies focusing on microplastics. I showed them, like from Song and Peng, what's published in Geology this year, a canyon in the South China Sea, where they found this 10,000 species per square kilometer. Then from Pier Domenico in South Italy, they looked at microplastics in canyon systems, which was also quite drastic, quite a lot. But microplastic, not that much, and especially then not looking at different regions and different sources to compare those. So we don't really have a good picture on where are microplastics in canyon systems and which canyon systems are particularly polluted by microplastics. This is something we need to find out, or we can. Yeah, it's also quite expensive to get these samples, though. Yeah.
Yes. So Florian, you have another question from Kate Gill. And do the plastic particles have the sort of electrostatic properties as in the glaze, or are they relatively inert?
I think it depends on the type of plastic. I mean, we have thousands of different polymers with additives, and I think this plays a role. They might have some electrostatic charges, which might also influence how they are transported. But yeah, that's all I know about that.
Yeah, so Ramon Lopez mentioned he is just throwing a question to the current discussion is about the effect of the geometry of the particles and should be considered instead of just density. The last question is from Giacomo Dalla Valle, and is I have a question for Celeste, and he couldn't follow your presentation entirely, but he is asking, I focus in the slide and say, you don't need excessive anoxia to preserve the organic matter. Is this correct? This concept could also make us rethink our idea that we have, for example, in the case of the sarcopelic deposits.
Yeah, so I did mention that at the end. I sadly didn't have enough time to get into that, but we have done geochemical studies throughout the section that I've looked at, and we found that the basin was under oxide conditions throughout this whole period of deposition. And even though it was oxide, I do see significant amounts of tidal filtrate in these sediments. And so it does seem that we can get quite significant amounts of tidal sequestration, despite the fact that the basin was oxide, even at depth. And that has to do, I think, with the rapid sedimentation. So levees have some of the highest sedimentation rates of any geologic environment, and that helps to just quickly filtrate these organic-rich sediments below the point to which they'd be able to be degraded or oxidized. And so in this way, it is possible to get these organic-rich beds without basin anoxia or other anoxic conditions.
Yes, so just to wrap up for this part of the forum, I would have to say that I like the comment Jacob asked, and I think this is going to be a food for thought for everybody, is that how do we convince the general public that dumping plastic in the deep ocean is bad, and combat any of out of sight or out of mind thinking, and how can sedimentologists contribute to achieve that? This is now becoming part of our task to do. So
I'm not sure. Yeah, what sedimentology can do, we can just highlight or show how bad it really is, and that it's not out of sight, out of mind. So it has an effect. It has an effect on different deep marine environment, on animals there. So I think this is what sedimentology can do. To really achieve that there's a different thinking, yeah, I don't know how much sedimentology can directly contribute towards that. We are more focusing on looking at the problem rather than at the solution. if this is, if you know what I mean.
Yes, for sure.
To use less plastics and to reuse plastics and to have proper waste management, and there's not much what sedimentology can do to that. But we can show where the plastic goes and what the impact of the pollution is, and this, yeah.
And to add to your point and kind of reference one of the things you're showing in your presentation, right, is, you know, typically when people are, you know, people talk about how bad plastics are in the ocean, they show those big garbage islands in the ocean. It's like, you know, like you said, it's like, yeah, that's an issue clearly, and you can see it, but it's only a fraction of what's actually being buried. And so I think one of the key roles is in appropriately diagnosing the actual problem that's happening, right? Before even kind of coming up with it, we're never going to come up with a solution necessarily if we think that it's, you know, a fraction as bad as it actually is, or where the source is, or hey, you know, if you look offshore this delta, there's not actually that much because it all got potentially whisked away or relocated by bottom current. So I think there's a huge role for the community to actually identify the genuine or actually refine and clarify our understanding of where these things are going and the impact that those have. And one of the points that I tried to make on this slide, where I kind of wrote some of the some bullet points, is I think the work that all four of y'all have shown already, or also already five of y'all have shown already, is that we need to more appropriately calibrate our models for carbon burial, for microplastics, and that starts with actually the model's never going to be right if we don't actually have any data to build the model from. And so I think there's a pretty huge role in terms of making the sedimentological observations that you've already been showing today. So I think that's really exciting to see, and I think that'll ultimately potentially unlock. There have been a couple questions on funding, new funding sources. Well, funding is going to be there when we start better understanding the problem. And so, yeah, right, there's a bit of a chicken and egg issue, but there's a lot of active work in the community kind of highlighting these issues. So I'm hopeful that the larger funding community responds because I think this work needs to be done.
Okay, so I am Jen Pickering. I am one of the new co-editors for the Sedimentary Record, which is SEPM. It's one of the publications that it's had for actually quite a long time, like 23 or 24 years at this point. Last year, or I guess 2020, Lauren Bergenheyer was the editor. In December 2020, Jung-Hyun Lee and myself, we took over as new editors, and we underwent this sort of transformation of this journal. So we wanted to transform it to a short format, high impact, peer-reviewed, diamond open access journal. And that's the key for us, is this is diamond open access. And that means that there are no fees for authors to publish, and there are no fees for readers to access the articles. So it's society funded, so SEPM completely pays for it, but it's community driven, meaning we do Twitter polls and that sort of thing, and we try to engage the community to sort of direct the journal. So we launched this renovation at the very start of 2021. So we're coming up on a year now. And what we've done so far is we reduced the operating costs and secured funding through one of these SEPM, an endowed fund that existed there. So we have funding to keep this a diamond open access journal secured for at least 3 years. The operating costs are at this point so low, though, that it's likely it will continue on indefinitely. We have sort of implemented this brand renovation. So we have a new submission and a peer review platform, which is called Scholastica. We have a new journal design and new article formats as well. And historically, TSR published 4 articles per year, so it was 1 article per issue and 4 issues per year. And we have no limits on how many articles we'll publish. So far, we've published 12 this year. We have 3 currently in review or revision, and as many articles as people submit and the reviewers accept, that's what we'd like to be publishing. So for 2022, we are switching to a continuous publication model. So there are no deadlines, and we'll do either 1 or 2 issues per year, depending on the volume that we get. Accepted manuscripts will be published immediately, so that'll be your publication date. And that's the plan for 2022. I'm telling you this today because the organizers here, Emma, Fabien, and Lilian, have proposed a special issue for the Deepwater Research Group, a special issue that would go into TSR. So I'm just giving you, the scoop on what's happening with us for that. So our submission platform, as I mentioned, is Scholastica. There's the website if anyone would like to check that out. We have 2 main types of scientific research articles. So we have research articles, which are high quality short format researcher review articles. We like these to be around 5,000 words or less, and that doesn't include captions or references, and something like 5 figures or tables. You'll notice the asterisks there. We are not strict about this at all. We really just want authors to be as concise as they possibly can, and we can't let it creep up into the range of a long format journal, because I think, as most people have probably heard, there are efforts like Sedimentology, which are longer format diamond open access journals. We want to stay distinct from them, so we are specifically short format, but it's not strict. And then we also have these early research advances, which is a new thing we've tested out. We've published one of these so far. This is really geared at early career people or students, or if you have a study that is, you've got some quality data that you want to share, but it's not really fully developed yet. These do undergo peer review, but we state to the reviewers that they're in the early stages. So these are kind of meant to get early feedback, or as sort of like an update, like if you find a stratigraphic datum or something like that that doesn't really warrant a full research article, but is something you want to get out to the community. We also do those. We also do editorials, which are not peer reviewed and are kind of separate from that. All of our articles are DOI linked. They're free to read and download. Right now they're at sepm.org/the sedimentary record, but I think within the next few weeks, we're going to be migrating over to Scholastica as a platform to host. And that's just because Scholastica has an integration with Google Scholar where they immediately get funneled into Google Scholar. And so, the articles themselves will get more sort of SEO internet traffic if we host them on Scholastica. So we'll be migrating to that. So the special issue that we're introducing here would most likely be hosted on Scholastica. We've also got a Twitter, we're at the Sed Record, and Rebecca Gramela sends out the SEPM updates newsletter each month. If you have any other questions about our new format or future directions, you can feel free to email myself or John Kuhn. Our emails are listed there.
Thanks for that, Jen. I really appreciate you taking the time to kind of showcase that. And building on that, like you mentioned, so one of the things that Lilian, Emma, and myself have been talking with SEPM and Sed Record about is trying to bring together and put together a series of articles or a special publication focused on exactly some of the topics we're discussing today, kind of, creating a platform to start publishing material on, the future of deepwater sedimentology and stratigraphy. There's a pretty big kind of intersection that's now starting to happen with a lot of new avenues of research, a lot of new technologies, as we'll discuss a bit today, and a lot more data collection and data creation. So we're kind of poised to actually, while there's a pretty, a lot happening in the community, we want the opportunity to actually build a nice special publication that kind of springboards a lot of the research we're seeing here today, a lot of the research that's being done by younger researchers starting in the field. It's a very different field to some extent than it was even a decade ago, or not 20 decades, but 20 years ago. And so we want, to crowdsource the community on the interest of this, on the interest of these topics that we're hearing today, and some of the next that we'll discuss in the next iteration of this in the spring. And feel free to email myself, Lilian, Jen, Emma, and kind of propose topics, propose ideas for papers that would be helpful on that. I think there's a lot of interesting work, and we want to make sure that it gets out, and also we kind of have a record on how we're proposing these conferences so that we can see the evolution of the work. So this allows us to start creating that benchmark to see that, hey, the topics we're discussing one year get put together and published and built on the following year, right? This is something that the scientific community strives for, and we're trying to do that with the topics here today as well. So definitely don't hesitate to reach out to us and focus on those opportunities as well.
Hi, so hopefully everyone can see my screen and hear me okay.
Yes.
So my name's Jess Hillman, and I'm down here in New Zealand at GNS Science. And today I'm going to talk a little bit about some of the work we've been doing on gas hydrates around New Zealand. So kind of quick crash course in case anyone doesn't know what hydrates are. They're essentially a solid ice-like form of water, where you have water molecules in a cage. In that cage, you're holding gas molecules. These are predominantly methane, but they can also be higher order hydrocarbons as well. And because they obviously contain methane, natural gas, you can set fire to them. So fiery ice is another name for these. They're found in marine sediments and permafrost. So obviously we're looking at marine sediments around New Zealand, but you do get them in permafrost on land as well. So the main way that we can find these is using seismic data. That's because predominantly where you find hydrates, they create a seal because they act like a cement or kind of like a glue to hold sediment together. That traps free gas underneath. Obviously, you have to have free gas somewhere to be able to form hydrates in the first place. And that free gas being trapped there creates a really nice density contrast that shows up really well in seismic data as a BSR. And the reason for that is that the bottom simulating reflection is that they are stable at certain pressure and temperature conditions, and so that basically means they follow the trace of the seafloor. So moving to New Zealand, we've done quite a lot of work around New Zealand looking at seismic data to try and identify where we find these hydrates, and they've been identified in quite a few places. So offshore Tasman, there's some indications of BSRs. There's an example here in the seismic line. There's also some indications of Pusica and Fiordland off the South Island to Waipounamu. On the Chatham Rise, we've been doing some work under a different project, which I'm part of, which is potentially looking at there actually being CO2 hydrates, so a little bit different to the more conventional methane hydrates. But today I'm going to focus on the Hikarangi Margin, which is offshore Tiko Maui or North Island. And here we definitely know these are predominantly methane hydrates. They're about 99% methane. So the Hikarangi Margin is New Zealand's largest gas hydrate province. It covers an area of about 50,000 square kilometres. You can see on the map here all those red dots show you where we've identified BSRs from seismic data. We've also got a lot of indications for active gas seepage, and we can see other indications such as pockmarks of potentially past seepage as well. And that was studied by Sally Watson, which came out in 2019. So the Hikarangi Margin is a very, very large subduction zone where the Australian plate meets the Pacific plate, and as the Australian plate is being kind of smushed against the Pacific plate, that creates a lot of deformation, and the overriding sediments get forced up into accretionary ridges. And there's a very strong connection in this area with the deformation of these sediments and where we see hydrate accumulation occurring. So in the last few years, under a program that I lead at GNS Science, we've had a really intensive data acquisition program in the southern Hikarangi Margin, so quite near to Wellington, where I'm based. And here we've been acquiring high-resolution 2D seismic data, so that's the black lines you can see on the map. And this has been, basically we've gone back to areas where we saw those indications for highly concentrated hydrate from existing seismic, so we've gone back and collected more focused data over those locations. We've also more recently added controlled source electromagnetic data in collaboration with Scripps. So that's the yellow lines you can see there. And we've also had some targeted biological surveys using both towed camera systems, sediment sampling, and a couple of ROV dives, which we're very lucky to get through collaboration with some US partners using ROV Jason and ROV Ropos. And this has actually allowed us to redefine the southern extent of the hydrate province offshore Kaikoura. So right down in the southern extent of this line, you can see there are a few patches of small patches of BSRs down there, and really extensive gas seepage at one of the sites where we've done an ROV dive actually earlier this year. So this gives an example of some of that high resolution 2D seismic data that we've been collecting. And you can see here you've got hydrate occurring within the apex of these anticlinal ridges. And these are potentially formed as a result of large thrust faults that soil out towards the deformation front. And that forces up these ridges, and they then become essentially a kind of structural trap. And we have a combination of factors acting here. So both the thrust faults bringing up deep source thermogenic gas, and then also shallower biogenic gas being created by microbial action within the sediments. And so there's a few different factors here. So both tectonics and the sedimentation patterns really control where we see these focused concentrated gas hydrate accumulations. We very rarely see hydrate forming in the interstitial basins. And there's a definitive pattern of it occurring along these ridges. And we actually do see it outcropping at the seafloor as well. So that image just shows an example from the larger ridge here, which is called Glendew Ridge. So some of our colleagues here at GNS have actually been working on whether we can test out this hypothesis that there's these different factors of the structural and the sedimentary kind of controlling the formation of the hydrate. And so we've been doing this using 3D modeling in Petramod, and that's been led by Carsten Kroger. So we had a paper out just recently on this. And this does demonstrate that we have these spatially variable rates of microbial gas generation within the shallower sediments. We also have significant gas recycling at the base of the hydrate stability field. But there is a significant factor still of gas migration coming up through these deeper faults, which then feeds into the deformed sediments within the ridges, and that kind of channels the flow essentially right into the apex of those ridges, creating that really concentrated, focused hydrate accumulation. And that's just, yeah, that's the paper that's out recently. We've also been looking at the connection between these hydrate accumulations and where we see active seepage at the seafloor. And that's for a few different reasons. We're obviously interested in what the structural controls might be, but we're also looking at the biological aspect, which I'll talk a bit more about in a minute. So one of the studies we focused on was a small ridge that creates, again, a kind of structural trap. And we know that there's a clustered normal faulting in the upper sediments. And so we wanted to see whether those normal faults were acting as conduits for gas flow, or whether there was something else at play here. And interestingly, at this site, we actually found that it's not normal faults that the gas is flowing along, even though there are lots of them, they're not being utilized as flow zones. What we showed instead was that there's this doming of gas right above an accumulation of hydrate. And the reason that's been able to form at this particular site is that we have mass transport deposits, which are stacked up through the sequence here. They're related to active deformation along the margin and these ridges being pushed up, and you have intermittent slope failure. And that mass transport deposit has slightly less permeable sediments contained in it, which actually creates a seal. So you can build up this accumulation of gas. Then eventually you reach overpressure, breakthrough occurs, and that's what's created this fluid flow conduit all the way to the surface. And we can still see gas seepage occurring at this location at modern day. And that was published just earlier this year by one of my colleagues, Gareth Crutchley at GMR. So this is just a little video of one of the sites we've been able to visit with one of the RVs. This is our RV Ropos, and this just shows that these seeps are, they are really active in places, and they're obviously linked to significant development of orthogenic carbonates, creating valuable hard ground habitats for organisms. And they're also known to be, these accretionary ridges and the seep sites are known to be focuses for trawling activity in fisheries, because they attract fish and provide ecosystem services. This is one of the sites that's been trawled quite heavily. You can see there's not a whole lot of life around the seep. There's a few kind of unhappy looking tube worms down the bottom of the image there. So if we go to one of the, if we go to one of the seep sites that hasn't been trawled, this is at a much deeper site. This is over 2,000 meters down. You can see the kind of life and the abundance that we do see in these locations. So really, really abundant tube worms, mussels, clams, other chemoaustrophs here. So these seep sites are supporting really significant ecological hotspots. They support really unique seep fauna. And these take thousands of years to establish. They don't recover quickly, so they're very vulnerable to damage from things like trawling. And the reason we were looking at this was particularly thinking about, do the hydrates play a role in slope stability here? And also what would be the potential impacts if we ever were to go ahead and produce hydrates for an energy resource? That's something that's very unlikely to happen in New Zealand, but we now have a really good understanding of what the potential implications could be. So we've been trying to basically document these sites and think about the shallower sites that have already been damaged. What are the implications of that? And moving forward, do we need to do more to protect these valuable ecosystem sites where they haven't yet been affected? So that was a very, very quick kind of crash course run through some of the work that we've been doing. And this is obviously work that's been done with a lot of people, both here in New Zealand and also internationally. So I just want to say thank you to all of our collaborators. And hopefully some of you found that interesting. And if you have any questions, I'd be happy to answer them at the end of the session. Thank you.
Hello, everyone. My name is Alexey Portnov, and I'm a researcher at the University of Texas Institute for Geophysics. And I'm very grateful to the organizers for this wonderful opportunity to talk about the gas hydrates in dynamic sedimentary systems. I know this is quite a general title, but I'll mainly focus today, of course, on the deep water sedimentary systems here. And I guess one of my major goals will be to show that we do have common grounds between the gas hydrate community and community of sedimentary geologists. So just for the introduction, gas hydrates are solid compounds of water and gas that are stable at high pressures and low temperatures. And actually, there are many places on Earth where such conditions are met, including the subglacial environments, including the permafrost regions, both onshore and offshore, and deep water submarine environments here. So in this video, you can actually see that hydrate does look a piece of ice, but it's not. If you set it on fire, it starts burning because it's a concentrated form of methane gas. So the upper part of the slide shows why and where we care about the gas hydrate. First of all, hydrates are climate sensitive, and this is mainly relevant for the Arctic regions. Hydrates highly depend on the integrity of permafrost and also thickness of the ice sheets, which in turn are controlled by the global climate cycles on Earth. So that is one of the major reasons I actually called my talk gas hydrates in dynamic sedimentary systems. Gas hydrates are also a geohazard. Whenever you want to drill through them, you have to be careful. But today we're mainly going to talk about gas hydrate as an energy resource, and that is relevant for the permafrost regions and for the deepwater submarine environments. Let's think about how the knowledge of deepwater depositional systems can help us finding and characterizing the gas hydrate systems. I've spent quite a lot of time during my career looking for such gas hydrate systems in deepwater environments, and I would say that my formula here will be quite simple. First of all, we're looking for coarse-grained turbidite systems, such as, for example, bird channel Levy complexes. That's where hydrates like to be at high saturations. Another important thing, and especially that's relevant for the Gulf of Mexico, we do like shallow salt bodies, obviously because they create those favorable structural frameworks in the salt roofs, such as four-way closures, and these are the classical traps for shallow hydrocarbons. And importantly, we are confined to this gas hydrate stability zone, which is typically about 500 to 1,000 meters below the seafloor. So it makes it easier to look for the gas hydrates. We don't have to have kilometers below the seafloor. And then if we have some methane gas in the sediments, either thermogenic or microbial, with a high likelihood, we can expect gas hydrates at high saturations. So now let me give you an example of such work that we have recently accomplished with the Ohio State University and the Bureau of Ocean Energy Management. And I acknowledge my colleagues here who really helped a lot to run this project. So we chose these 5 project areas in the deepwater Gulf of Mexico, and we were looking for new gas hydrate reservoirs in coarse-grained turbidites. We used public, free 3D seismic data, which is green here, and also well log data, which is red dots here. Our first goal was to use 3D seismic data and seismic attribute analysis to map the channel EV complexes and some shallow salt bodies in the regional scale. This map on the left shows the root mean square amplitude attribute, how it highlights the channel EV complexes approximately at the base of the gas hydrate stability zone, where the chances of finding gas hydrate at high saturations are higher. There's another channel EV complex here, and these are actually the areas where we did find some promising gas hydrate reservoirs. The map on the right is an example of a more complex map where we actually show the results of the interpretation. The color here, like white to green, shows the depths of shallow salt bodies. Above that, the yellow semi-transparent color shows the trajectories of the channels, and the red semi-transparent colors, like here or here or here in each of those zones, are the BSRs, or bottom simulated reflections. These are the first order indications of gas hydrate in the seismic data that I will show just in a second. Now I'd like to zoom into one of our most promising findings, which we named the Moby Dick gas hydrate system, and it's located just south of Louisiana in 1,500 meters of water depth. And this is an excellent example when several components that I've talked about earlier, such as, for example, salt core anticlinal fold and the channel Levy complex on its flank, they all came together well. Apparently, there's also methane gas here. So the seismic data shows the channel Levy complex between these 2 dotted green lines, and it is also confirmed by a low gamma ray in the nearby well. Importantly, we do see here a very clear trough leading or negative polarity BSR that cross-cuts the entire 200 meters thick channel Levy complex. Even more importantly, if you follow my pointer right now, you see that we're moving along a sand-bearing layer, which is blue or peak leading above a BSR, and then it changes its seismic response to trough leading or negative polarity below the BSR. And we interpret it as gas lag below the BSR and hydrate above the BSR. In fact, if we map this strong peak leading reflection, we can map the extent of the entire gas hydrate reservoir. At the Moby Dick, as well as some other gas hydrate systems, the quality of the 3D seismic data actually allowed for a more detailed characterization of those systems. And in this case, you can see how this channel Levy complex is actually meandering pretty nicely from south east to northwest. And here in the 3D reconstruction, I'm showing the 3D seismic, which is flattened along the basal horizon. And I also blanked the seismic data above the paleo channel surface. So this is not the modern day seafloor. And this allowed me to actually see where our gas hydrate reservoir is located relatively to the elements of the channel Levy complex. And this probably may help to better understand the lithology of the reservoir. Okay, so now back to a larger Gulf scale, and in the end, well, first of all, I hope that I managed to show that the knowledge of deepwater sedimentary depositional systems is extremely important in the gas hydrate research, and we do share many common interests. And also, I would like to say that all of the data that I've shown today and many, many more are now publicly available at the BOEM webpage, as well as in our recent papers here. And I guess in the very, very end, I just would like, well, answering the question, what is the future, right? So I do believe that there is a big potential in further developing of similar projects on the margin between the gas hydrate research and also the research of deepwater sedimentary systems. And especially this is relevant because there are more and more public data that are being released, and we're expecting more high quality data in the deepwater Gulf very soon, and that also happens worldwide. So there's definitely more questions that we can ask and answer in the future. It was a great pleasure for me to present on this Deepwater Forum, and if you have any questions, please feel free to contact me here, and thank you for your attention.
Excellent presentation, Alexei. And again, I think, you know, the last two talks, it's pretty interesting to see that, again, you know, there's a lot of publicly available data and, you know, an emerging energy resource, but also clearly a hazard. And like Alexei was mentioning, you know, there's a lot of commonalities with the work, you know, that the deepwater sedimentology community does. I think it's exciting to see that they're also relatively shallow systems. So they might be the systems that we're also imaging really well to kind of study there. So now kind of pivoting, over the next two talks, we're kind of going to move into the realm of forward stratigraphic modeling and what we can leverage those types of models to actually do to better understand our deep water system. So go ahead, Peter, and again, thanks for presenting.
Yeah, thanks for the invitation to join you and present. It's great. I'm going to talk about a couple of different bits of work, but for the bulk of it, the modelling stuff at least, just need to acknowledge Alfie and Chris, colleagues in Liverpool who I've been working with. So what I'm going to talk about is basically this, two things: sediment routing systems, specifically the issue of how wide are shelves, how wide have they been in the past, and a few examples of numerical experiments, so using stratigraphic forward models in an experimental way. And I'll kind of show by example what I mean by that. Neither of these things are actually new. So, I mean, we knew about sediment routing systems and how important they were back in the mid-1990s onwards, right? But I think in the context of the future of deepwater sedimentology, both of these things are still important, and there's still mileage, kilometerage to get out of both of them. Okay, so hopefully I can demonstrate why I think that's the case. So talking about sediment routing systems first. So a key issue in this in sediment routing into deep water is how wide are the continental shelves, because they present a buffer to the transfer of sediment from river mouths into deep water, right? You probably all know this very well. And most shelves now on the planet are pretty wide. I mean, you know, up to a couple of 100 kilometers wide, where you've got river systems feeding into them, and in some cases wider for tectonic reasons. I mean, it's quite complex. But basically, that's a lot of that wide width is a consequence of very rapid Holocene eustatic sea level rise, glacier eustatic. Now, we know from paleoclimate records, reconstructions, with which there's a fair bit of uncertainty, but we've still got a pretty good idea that kind of ice house setting that we've had for the last 2 million years or so is relatively rare. It's not happened that much through Phanerozoic time. So this kind of raises the question, and what did greenhouse shelves look like? So in other words, what did these shelf settings look like when the climate was much warmer, when sea level wasn't going up and down at the same kind of rate? So here's our kind of hypothesized difference. The top diagram here shows wide shelves. Gray is the marine strata and greeny yellow is terrestrial to shoreline strata. So you can see these sort of wide stretches of marine shelf that extend over a large part of the top of the delta cliniforms that form the continental margin. And what we're arguing is that the greenhouse morphology may well have been much more like this. Okay, but of course this is so much narrower. You can see these stretches of marine shelf are basically much narrower than in the icehouse setting. But this is just a hypothesis, right? So how do we test whether this may have been the case? So working with Ron Steele and Jinyu Zhang from BEG and University of Texas Austin, we've essentially measured examples of these systems, okay? And without going into lots of detail, we've got, I think, about 10 different systems and you know, several cliniform measurements from each. This spans a range of basin types, a range of different scales, different cliniform geometries, and most importantly, three different climate settings, essentially greenhouse, icehouse, and transitional. And you can see they're listed here in the set. And our method is essentially based on either well log, outcrop, or seismic data to try and reconstruct how far those marine stretches of rock extend into the top sets of the cliniforms. That's essentially what we're measuring. Now, when we do
Excuse me, can we, sorry that I have to interrupt you, but it's, the setting that you have right now is in notes setting, so could you change into the full screen setting?
Yeah, I can do that. Yeah, it's just, I think it's just because they're on.
Just go, yes, go right on the display, yes.
That better?
Perfect.
Okay, cool. Sorry about that.
Sorry.
That's just in the nick of time because this is a busy diagram, so it's good to have it bigger. So this is the result of the study essentially, and what the takeaway points from here are that we've got 70 million years of geological time plotted on the x-axis, and then we've got the sort of the width of the total top set of these cliniform systems on the vertical axis, but normalized, so it goes 0 to 1. And what we're showing here is data from greenhouse systems, transitional systems, and icehouse systems. So green is greenhouse, yellow is transitional, blue is icehouse. And the takeaway point is that the mean widths for the greenhouse systems are substantially less than for the icehouse system. So this is what these data are telling us, right? So mean icehouse marine shelf width is significantly higher as a proportion of the total topset width than the greenhouse equivalents. So think back to that cartoon, it is pretty much like we drew it there. That does seem to be the case, at least for this data set. So we need to expand the study and probably look at more examples, and there are a few issues that probably need to be further explored. But I think what this poses as a question, you know, thinking of the future and future researchers, then what then are the consequences of this for greenhouse Cretaceous, for example, age submarine fans versus, you know, Pliocene, Pleistocene submarine fans? The latter are not necessarily a good analog for those older systems because the narrow shelf is potentially going to make a big difference. So there's quite a few questions that are raised by this that I think are going to be exciting to pursue. Okay, so that's that. Now, numerical experiments then. This we've done, we've been doing these experiments using a couple of different models that we've developed over the past couple of years. So this is low-byte 2D and low-byte 3D, one being two-dimensional, the other being three-dimensional. They're both reduced complexity models. So Isabella Maciero, a former PhD student in Liverpool, myself and Alfie have been writing these codes, all deterministic, very simple, reduced complexity. They model sediment transport in a very simple way, but the really nice thing about them is you can model lots and lots of flows. So because they're simple, they run fast, okay? But they also do bed by bed detail. So this is important. So on this diagram, for example, each of those little red, orange, yellow layers, that's equivalent to one sedimentary bed. And a lot of stratigraphic forward models don't really resolve things at bed scale. They're more sort of general, you know, diffusion based, for example. They tend to be thicker intervals of not really bed scale strata. So this is quite useful to have a model that runs in this way. And I won't dwell on all of the maths and so on, but I just put this up to show you that it's reduced complexity, but physically reasonable. The essence of it is that flows move down the steepest descent route down a slope, and then when they hit a gradient threshold, they change from eroding or bypassing to a form of dispersive flow. Okay, and the erosion is modeled using some pretty classical equations, which give us some interesting behavior, but are very simple, you know. And the deposition is basically just spreading out of the sediment to form a lobe. So what kind of things do we get? Here's the gist of it then. The 2D model, what I want to show you here is just two examples, right, which illustrate what I think could be a potentially significant point going forward. So there's a top model here, and you can see that here's all the layers of the beds that are produced by the Lobite 2D run. It's about 200 flows, okay? And this is the lower one. The second model is the lower diagram here, which is also 200 flows, but has got slightly different parameters, so a slightly higher erosion rate and a different grain size, okay? And the difference between those two architectures, you can see this is much simpler. It's basically very straightforward mounds. You can probably just about see lots of backstepping of deposits accreting on the back of a slope here as the flows come down and hit the topography and deposit, and effectively that drives backstepping. This blue-red diagram is a chronostrat version of that cross-section. So you've got distance versus the number of flows, so effectively time. Blue is deposition, so you can see that mound corresponds to this big blue blob, and that backstepping there corresponds to this blue wedge, which is diachronously backing up the slope, right? The point about this, though, is it's pretty simple. Solid areas of blue, solid areas of red, solid areas of bypass in between, right, where relevant. Okay, now, compare that, though, with this. This is much more complicated, okay? Simply by changing one or two parameters, we've switched from something that's quite simple to something that's much more interaction between the flow and the topography. It's much more complicated. There's multiple zones of bypass, erosion. There's a lot going on in there. We can characterize that with this SE thing, spatial entropy. Alfie just very excitedly sent me an email earlier saying that he'd got the code working so we can calculate the values. Basically, the spatial entropy is higher for the more complex version, and that's all you really need to know. Okay, so what this is showing us is complex strata from a very simple model. That's why I find it particularly interesting. The model couldn't really be any simpler. I mean, well, it kind of could, but it couldn't do anything interesting and be any simpler. It's pretty much as simple as it can be. And yet this contrast and that complexity I find actually fascinating. And I'm really looking forward with Alfie to actually exploring this further. He will be talking about this at BSRG in December, which is a UK Sedimentology conference. I think it's going to be at least partly online. So if you're interested, you can see more about this then. Now, just to finish off then, the 3D version, this is Lobite 3D, and we're doing similar kind of numerical experiments with this, but sort of related but slightly different focus. And here, I'm just trying to understand the nature of lobes in this kind of very simple fan strata, right? So you can see this is a picture of a Lobite 3D run. You can see lots of the individually colored flows there are the different shades of red and orange. You can see this is the channel system that comes down the slope into the fan and then into the fan. And then each of those little blue dots is a apex point for one of the flows. And you can see they backstep up, they backstep up channels basically, and then fill the fan as they go. This is an example of the stratigraphy produced. You can see nice trends of thinning upwards beds. But the key point here is that there are lobes, what really do look like lobes developed in this cross section. So just expand on that a second. Let me just see if I can play this. Can you see that animating? So this is a run through of the model, a lot of those strike sections. So we're moving down the fan from its proximal apex towards its distal end. And you can see, if you look, there's a series of lobes here developed, separated by these muddy units. The grey is mud, by the way. The red and orange, again, are the individual flows. This is the chronostrat version of that. So you can see nicely separated in time, discrete. groupings of the sediment that are effectively like lobes. Oh, sorry, I didn't mean to play that again. Let me just move on. Okay, so it looks like there are lobes in the model, but what I'm interested to try and do, what we're interested to do with Chris and Alfie then is, can we actually convert that sort of, they look kind of lobey, into something that's a little bit more quantitative? So this is my first attempt, and this is still very, very much in progress, to try and actually define how we would identify a lobe in this model output. So we've got a little flow chart that essentially calculates, when the model run is done, where the lobes are based on the position of one flow after the other, okay? And I won't go into the details of how it does it, but it's basically the position of each flow and whether or not the flow is separated from flows underneath by some sort of mud-prone hiatus. So, I mean, it's kind of what you would expect as perhaps a reasonable definition. And when we do that, we get something like this. Right, so the colors here are showing the different bits of sediment that have been classified as lobes. But interestingly, it's not actually straightforward. Even with that algorithm, it doesn't work as well as I thought it would. There's more complexity in here than you would first think in terms of how the different flow accumulations, if you like, the different lobey type bodies are connected to each other. So it's quite difficult so far, at least, to quantify exactly what is a lobe, define it in numerical terms, and then have the computer identify it automatically. This plot, by the way, is lobe volume through time. So it's how these lobes have grown. And you can see what happens is they grow very steadily and then stop. And that happens to some of them. And there's three bigger ones that are dominant. That's the brown, the green, and the sort of orangey color one. But then this red one is a bit more intermittent. It sort of grows, stops, grows, stops. So what we're seeing here is that there's a bit more going on than perhaps I would have first have imagined, even in a simple model. So here's running the model forward through time in plan view so that you can see this is the first lobe growing. And I think hopefully any second we're going to have an evolution. There you go. So you start seeing other things happening. And what seems to happen is there's almost like a transition period whilst the model tries to find the system tries to find a new sort of stable setting, which it then fills from, and then it switches again. There's another bit of instability, and then the next lobe sort of stabilizes and goes. So this is quite interesting dynamic behavior that we're now trying to explore and understand the consequences of. Okay, oops, I've done it again. Let me just move on. And what we also see is that if we run the model for longer, so 1,000 flows, it just gets more complex. As the basin floor topography develops, as you might expect, the interactions between the flows and the topography also develop. And it you can see that there are lobe-like things in here, but again, to define them explicitly numerically is surprisingly tricky. Okay, and I'll just very quickly run through and show you some of the complexity of this one in 3D as we scroll through it. And if you watch carefully, you can see that it looks like some of the lobes merge into each other and get more and less distinct as you move through the system. Okay, so there's a lot going on here. And remember, it's a reduced complexity model. So this is complexity arising from pretty simple inputs and very simple physics. Okay, because I can't code complicated physics. Okay, so, and then the lobe classification in this case looks like this. I mean, there's a lot of colors in there. And when you look at the lobes through time, I mean, it's like some sort of very complicated nightmare subway diagram. You'd have no way of finding Piccadilly Square on this subway map. Okay, so the takeaway message is there's a lot of complexity in a simple model. Even in 2D, that's the case. When you take it into 3D, you start to get the sense. So this is making me wonder about our definitions of what lobes are, particularly this idea about a lobe hierarchy. I'm not really seeing anything in here that could be classified in any way as a hierarchy in the sense that it's drawn in the standard sort of cartoons that are published. Okay, so one final slide, results. And this is something I've shown a few times before, because the other thing that we're doing with this model is to try and understand how signals are preserved in this fan. It's a long story, been working on it for a few years, and it's surprisingly complicated. It's complicated because doing the robust time series analysis required to actually say with confidence when a signal is present and when it isn't is much, much, much more complicated than I think most people really, you know, explain in the literature. It's very hard, particularly when you're trying to do it across a couple of thousand model runs consistently in a way that allows comparison. Okay, so we're kind of getting hints that it's actually the short duration signals that are preserved best, which is counter to quite a lot of what's published, but this needs quite a bit more work. But it is something I think that this kind of modeling will shed more light on as we go forward. So here's my summary. The future of deep water sedimentology, at least the contribution that I can make to that with and Alfie and Rob and Ron and Ginu and the rest of us, right? Narrow shelves, thinking about the sediment routing system remains at the center of what we do, I think, in terms of understanding where the sediments come from, how much is going to go into deep marine settings. It remains a critical question. And then numerical experiments, I think these are going to be increasingly useful as we go forward, whether they're really detailed physics-based models or whether they're reduced complexity, things like this. There's a lot you can do with them. If you take an experimental approach, and that's something I would emphasize, run experiments with these models. Don't just run models to match them to outcrops. I don't think there's much point doing that, but if you run experiments with them, you can do all sorts of interesting things. Okay, so that is the kind of the last point. If simple numerical models can create complex strata, what is this actually telling us? Presumably the real strata are even more complex, and maybe we're just not really seeing that complexity in a lot of our conceptual models as much as we should. Okay, so that's it. And finally, I just put this because this is my favorite cat picture off the internet, the missing cat that isn't. Okay, thank you.
Excellent talk there, Peter. And yeah, definitely, I think there's going to be a lot of interesting discussion again about this. I think you're right. I think what can be done with forward models is it's an exciting avenue for sure.
Okay, thank you very much, and thanks for the invitation to present here. So I'm Alex Normando. I'm a researcher with the Geological Survey of Canada here in Halifax, Nova Scotia. And today I'd just like to present some of the new research we've done over the last few years on the influence of cryospheric processes on marine geohazards. Apologies, I'm trying to switch slides here. Okay, so submarine landslides. I'll mostly focus on submarine landslide, but you'll see that there's some applications to other types of geological hazards. So submarine landslides are often orders of magnitude larger than their terrestrial counterpart, and as such, they represent major geological hazards. Now, the image here in the background is not to scale, but it's just to show what a submarine landslide looks underwater. And so these landslides can be a threat to coastal communities because they trigger tsunamis and also offshore infrastructure. So the triggers of submarine landslides are often identified through the use of cable breaks, repeat bathymetric surveys, and acoustic Doppler current profilers. However, that's mostly done in non-glaciated settings, so further down south, because it's very hard to monitor sedimentary processes on the seabed in glaciated margins in the Arctic or Antarctic, just because of resources and how far it is. So in these glaciated settings, many interpretations of the triggers of marine geohazards rely mostly on sedimentological analysis of their deposits. But we know that that's not very reliable from studies further down south. And so in glaciated settings, we also know climate change is leading to abrupt changes in the cryospheric processes. So there's melting glaciers that's bringing a lot of sediments to the coastline. There's a reduction in sea ice as well, thawing permafrost that has consequences both on the coastal environment, but also in the marine environment, and also a rise in sea level. And these changes are really modifying the coastline in drastic ways. But how does that affect the marine environment? We kind of know a bit about how it affects the marine environment where we have seafloor mapping, and that's where we're lacking a lot of data. So regional seafloor mapping is really critical first step to identifying the distribution of marine geohazards to see if there are submarine landslides or turbidity current channels in areas. But it does not really allow us to understand what causes them, because the problem is what we map on the seafloor happened in the past. We're not observing a new phenomenon in action. So that's where there's been a lot of efforts in the last decades to try to monitor and use repeat seafloor mapping to link marine geohazards to modern changes, in this case, in the cryosphere. And so just like on land, we were lucky enough with the advent of satellites that we were able to monitor changes in the cryosphere, but also on sedimentary processes on land. We don't really have that yet for the marine environment at the global scale, but we are trying as a community to map some regions, some selected regions, to try to understand what's happening on the seafloor in light of these changes in the catchment scales or in the cryosphere. And so this leads me to just a case study of a fjord here in Baffin Island, and then I'll try to extrapolate those results to Continental Margin, and we can then discuss from there. So the case study that I'm going to present here is from Southwind Fjord in Baffin Island. So that's the red dot we can see here. And the reason we went there is that there was regional mapping that was done before in that area in 2013. And that's the multi-beam bathymetric map that we can see from that fjord. And what was really interesting is that you can see that there's a channel coming down from the fjord head deltas here. So we're pretty sure that there are turbidity currents that are occurring probably every summer. And there was also a large number of submarine landslides that we can see here on the sides, and we can see it in the zoomed in image here. And so we thought if we want to understand what causes submarine landslides in Arctic regions or glaciated regions, then that fjord becomes really important because it seems to be pretty active. And so we were lucky enough that we started a short monitoring program over a few years. We deployed ADCPs. We had some issues with them, but mostly we did repeat seafloor mapping. And we were lucky enough that we actually saw something happening on the repeat seafloor mapping. So this here is on the right side is from that square here. And we can see the data, the multi-beam data in 2013, and we can see that the seafloor is relatively smooth here. And then when we remapped it in 2019, we can see the change there on the seafloor where there's a new submarine landslide that happened. Now it's a small scale landslide, but it was still a good example to try to understand, okay, what happened between those years. So I'll just go back again, 2013 and then 2019. And then if we do the difference in elevation between these two surveys, we can see in the white spots the erosion caused by the landslide and the deposition at the base of the landslide. Now, we also had data in 2018. Unfortunately, the data was not as good as the 2019 and 2013 data. It was with a lower resolution multi-beam echo sounder, but it still allowed us to see that there was a deposition of 3 meters between 2018 and 2019. So we were able to see that that landslide happened sometime between our survey in 2018 and in 2019. So that offered really a unique opportunity to understand what causes submarine landslides in glaciated settings. Now, the first thing that we saw also on the new data after the landslide happened are these iceberg pits at the head of the headscarps of the submarine landslide. So you can see here the slide scarp, you have the headscarp here from a side view, and you can see those iceberg pits here and here. So we thought immediately, well, would it be possible that these iceberg pits caused the landslide? So again, we went back to the bathymetric surveys before from 2013, and we could see that there were no iceberg pits in that circle there that we see. And then in 2019, these new iceberg pits that are there, and so we thought, well, most likely those probably triggered the landslide. So then, of course, we want to prove that even more. So we went to satellite imagery, and that's where, again, if we have repeat satellite imagery, you can start understanding the processes. And so we could see icebergs coming in and out in the fjord in August 2018. And then in August 27th, we can see an iceberg coming and then grounding early September at the exact location where the landslide happened. And so we'll just focus a bit more on that, but just as an anecdotal before, is that actually on August 27, 2018, when we can see that iceberg coming in the fjord here, if we zoom into this location here, we can see that that is actually us on a research cruise in 2018 collecting the data for this study. And so that's the Canadian Coast Guard vessel Hudson. And so we have also some drone footage where we can see our vessel here and us doing some surveys, and then the iceberg in question just at the back here. So we actually had some measurements of that iceberg coming in the fjord at that time. So incredibly lucky coincidence here. And so if we zoom in on what happened in early September 2018, this is what we have. So here is the hillshade image of what is assumed to be the seafloor on September 4th, and then some transparency. So the white dot here is the iceberg that we just saw on the satellite imagery. And so on September 4th, the seafloor is assumed to be stable, or there's no landslides. And so icebergs are coming in and out and then grounding in that location. And then on September 9th, something happened, and I'll just go back again, and you can see that the iceberg actually switched position. So it seems like the iceberg actually flipped, so capsized, and then impacted the seabed exactly here at the location of the landslide, and also split in two. So you can see another iceberg here. So that split from the original iceberg that impacted the seabed and caused the landslide. And so this is, then that iceberg stayed there for a month or so afterwards. And so we have quite good evidence that icebergs here triggered a submarine landslide in this fjord. Now, can we extrapolate those results to continental margins? Can we see some evidence of iceberg triggered landslides on continental slopes? And so we started looking at what is the modern distribution of icebergs originating from Greenland and from Antarctica. And the yellow line there that you see is the shelf break, essentially at 500 meters water depth. And that's also the maximum depth of modern icebergs in Antarctica and Greenland that have been measured in the past. And so wherever that line, that yellow line intersects the red zone is where there's potentially iceberg triggered submarine landslides. And so of course we're missing a lot of multi-beam bathymetric data in those locations, but where we do have some data, as for example here on the Scotian shelf, so just offshore Nova Scotia, we can see series of bottleneck submarine landslide coming down the continental slope. And that's starting in approximately 200 meters water depth and extended to 1,000 a meter water depth. And those extend for kilometers downslope also. And what's fascinating here is that they originate from single individual iceberg pits, as you can see here at all these numbers that we see along the margin. And so if we focus here on 8 here, and we'll just look at that example, we can see that there's an iceberg pit here in the multi-beam image, and then a bottleneck kind of landslide going down for multiple kilometers. And if we look at profiles across this, we can see here on the right that the iceberg pit has a depth of about 8 meters, and the failure plane depth of that landslide is about 10 meters. And so it seems like the iceberg probably capsized, or maybe it's a nice sheet whenever that happened, where there was a collapse of a big iceberg and then hit the seafloor and generated those landslides across that margin. Now, interestingly, also, we see a lot of iceberg pits at canyon heads in that region and along in a lot of regions where there has been glaciations in submarine canyons. So we're also thinking, well, is it possible that icebergs that hit the canyon heads create submarine landslides or turbulent currents that then flow down submarine canyons? That's an open question. We don't have an answer for that, but the relationship here is quite interesting. And then just another example here, that's from a study from Steen and al. 2016, and that's on Lomonosov Ridge, where we can see those lineations. Those are glacial lineations, and we have those submarine landslides on the scarp there. So is it possible that there's a relationship between the glacial lineations there and the slide scar? The question is still open. And so I'll just finish on this image here and a couple questions. This is an iceberg that we can see here on the left side. That's A68 coming from Antarctica, from the Larsen Sea ice shelf that broke in July 2017. And then it navigated along the iceberg alley there in Antarctica. And there was a lot of talks in February because it was going to hit South Georgia Island that you can see here. So there was a lot of talk about the ecological consequences of that. But what would have been the marine geological consequences of these giant icebergs breaking from Antarctica and hitting the continental margin or the slope around South Georgia Island? And has that happened in the past, and has that created a landslide in the past or not? And so I think there's a lot of studies on modern slow processes in Antarctica that could look at these types of processes. And then the other question is what other triggers of submarine landslides are we missing due to lack of repeat mapping and monitoring data? We were just lucky enough to be at the right place at the right moment for finding that iceberg can actually trigger submarine landslides, and that wasn't really known beforehand, or at least was never observed. And so what other processes are we potentially missing just because we're not looking or doing this repeat mapping that we can do online with satellite imagery? So I think there's a lot of work that needs to be done towards the monitoring and the repeat mapping to try to observe these processes rather than interpret them from sediment cores. So on that note, I'll just like to thank quite a lot of people that are always involved in these research crews. As everybody knows here, those are quite collaborative crews that requires a lot of people on deck helping out. So thank you, everyone.
So we're going to jump into another section of kind of Q&A and discussion. I know we're kind of at the end of the time we planned, but I think there's enough people that are interested that we want to keep going and kind of actually have that discussion. But before people, if people can't stay and they have to go, I want to thank all of the presenters up front already for some fantastic talks. Thanks for taking the time to put together that material and present it. The work was incredible. Also, thanks to Cassie for all the logistical support, SEPM and Jen, and again, huge shout out to Lilian and Emma that put in a huge amount of work to get everything set up. So thanks again for that. There are quite a few questions that are starting to show up, even though my computer is going a little slow. But one thing I'll kind of bring up again to generate more discussion is I just want to share one slide that kind of tries to summarize a couple of the key points that we want, again, just really wanted to emphasize. So I think one of the key points of this actual session of this conference, right, was to kind of illustrate the ongoing work that is kind of creating that platform for the future directions of deepwater sedimentology and stratigraphy, but also, get that dialogue started. As we saw from that poll, right, there's about a third of the people, have concerns over the future of deepwater sedimentology and stratigraphy. And so I think, it's hard to see the talks that we saw today and not get excited about a whole slew of new topics, a whole slew of new techniques that we can actually use to challenge some long-held assumptions, create some new hypotheses, and actually create that that new knowledge. And so already what we've actually seen today, right, is that there's a whole bunch of, there's a lot of work that's being done on trying to better understand deep marine processes, understand that they're dynamic and interrelated, and actually we might have to build new conceptual models, new depositional models to address those, right? We also saw some pretty excellent work that was focusing on the transport and burial of both modern organic carbon as well as microplastics and pollutants. So there's again, a lot of outcrop work, modern work, ancient work to understand where, from where those sources are coming from and where they're stored, how much. There's a whole amount of work that can be done on better understanding hydrates and kind of bringing together those fields of hydrate exploration from a future energy resource and a drilling risk perspective, and kind of how that merges with deepwater sedimentology and stratigraphy. And then we saw work on forward stratigraphic models and the ability to kind of data mine them as a digital analog that we can actually access in a way that's easier than walking through a really hot outcrop location. It takes time and we can't quantify things in the way we want to. And then we saw some work on submarine landslides, right? These present geohazards. They also present, the sources of some of those sediment gravity flows that we're trying to understand where they then go and deposit. So I think there's a huge amount of interesting work in terms of topics, but also what was kind of consistent throughout, I think, all these talks, and after that I'll stop, is just that how all these topics are also intersecting the fact that we're seeing, rapid rates and high volume of data collection and data creation, whether that's digital analog data, whether that's modern seafloor data or satellite imagery data. This is also coinciding with much more accessible tools for data analysis, and we can use those in conjunction, right, to kind of convert those analytics into insights that might actually help us develop those next gen concepts. So I think there's a lot to be excited about. Hopefully that kind of also steers in some ideas on some of the questions. I see a few right here. So for the presenters, can you all turn on your cameras again? I think for everyone that would be good, not just if you're being asked a question right now. So the first question that popped up on my screen was from Ramon Lopez, and it's for the presenters on gas hydrates. And the question is are you aware of the facies/sedimentary structure models that could be used to recognize structures in ancient outcrops created by the migration and escape of gas hydrates? Are there any publications on this, and could you share those that you think are best? He's found a few, but not really convincing because of a lack of real world data. I think it's a really interesting question. Jess and Alexei, you know, take it away if you've got some ideas on that.
Hey Jess, hey all. I think I can start really briefly, like just throw an idea, and if you have something else, just jump in. So let's just to clarify, we're talking about the traditional terrestrial landscape, right? Outcrop onshore. And we're trying to understand if there was hydrate in this, let's say, sediment package or not. If that is the question, then the first thing that comes to my mind is we have to understand that well, hydrates are not stable at the atmospheric pressure. So it means at some point they have dissociated, and this point is when the sea level dropped below about 500 meters of water depth. What happens then is your hydrate dissociate at the seafloor, creating the pockmarks, and also there is this biogeochemical process called the formation of autogenic carbonates, and those are pretty thick carbonate crusts. And that is the great evidence for ancient methane seepage. And if that can be connected somehow to hydrate dissociation, if these carbonate crusts at some point were exposed to the subaerial environment, and then we can see them in the outcrops, and that happens, and there are papers on that, and I can definitely send a couple of papers about that. And that's my first kind of big point that I wanted to share with. I don't know if Jess can think about something else.
No, that sounds about right. So generally, you're not going to see evidence directly for the hydrate having been there, because obviously, like Lexi said, it disappears. You might see the fact that hydrate can act like a cement, so potentially you could see some alteration factors, and that it might be that you've had a layer which was more resistant to erosion. But I think it's the combination of looking for things like the dissociation features, so maybe pockmarks, maybe autogenic carbonates that relate to seepage associated with hydrates. But of course, they can also be formed just through free gas coming up, not necessarily just hydrates. So a combination of that plus thinking about what would be the paleo environment. So what was water depth? Would it be the right conditions for hydrate to have been there in the first place? And there are also obviously geochemical indicators you can look for. So you can look at things like the carbon isotope composition. Does that fit with what you'd expect for hydrates? And there's some work being done in things like lipid biomarkers, and using that as actually indications where you've had dissociation of hydrates in the past. That's not my area of specialty, so I'm probably not the best person to advise on it, but there are publications around there.
Excellent. All right, the next question we got is from Brian Romans. This is to Peter. Very interesting study/hypothesis on the greenhouse versus the icehouse shelves. How should we think about the inheritance from previous phases? That is, shelves are constructed over long periods of time. Have you looked at trends when accounting for the overall duration?
So yeah, it's a good question, Brian. I think the simple answer is no, we haven't looked for that yet, because I'm not sure there's enough data in the examples that we've got to really do it in a meaningful way. We've got like 8 or 9 systems. I don't know that they span enough different systems to really get a grip on what you're saying. I mean, in theory, I think we can say that that kind of inheritance definitely will have an effect. But I wonder whether it's maybe at a slightly larger scale. I mean, we can show from modeling studies that, you know, cliniform shelves may lock themselves into a certain width after a certain amount of time, because it's hard for them to prograde beyond the steep slope once it really gets established. So that's going to have some impact. But I think to say more than that at this point, we probably need more data to analyze, which I think, you know, is kind of the next step planned for this work, really.
Those are good points. I think I just lost my list. Oh, okay, so the next is from Tim Demko, where he says that numerical models provide omniscient information on not only the deposits but also those flow processes at every node and at every time step. So his question, I guess, is then, should we be constrained to terms for classifying model results like hierarchies of channels, levees, lobes, which are derived from deposits in geomorphology? Could we use the omniscient process information, shear stress, concentration, criticality, etc., to classify new ways, or to develop new ways to classify model results and maybe real deposits? I guess, you know, Ali and Peter, y'all both have, I'm guessing, some thoughts on that, and I have a few as well, because I think it's an exciting avenue.
Yeah, and I think my talk related really well with Peter's talk of just now that we have access to a lot more information and, you know, the underlying processes that build these products, it does make you question, well, what is a lobe element? How do we, you know, do our definitions of that hierarchy actually hold up when we can now go and examine and test those hypotheses? So I'm glad that that was kind of coming across. And I think that these results, both just examining these model results and then also quantifying these metrics, I mean, even clustering these metrics, I feel like is kind of useful just to see, okay, well, does this break out in a map view, you know, distribution of how we might actually think of these systems? And then thinking back to, okay, well, now if I'm using net to gross or amalgamation ratio and I'm interpreting a well, you know, would that well actually fall in the location, or how unique is that well pattern now that I can compare it to thousands of other well patterns across different environments? So I think definitely using these results to kind of challenge that idea and challenge our existing framework and how we've approached interpretation up to this point, and not being constrained to the framework that we've built, but maybe approaching from that point of view of, okay, well, this is what I think an element should be. Now let me go challenge that or test that. And so I think that's kind of what Peter's talk was pointing to as well.
Yeah, exactly, Ali. I agree. I mean, one thing though is that in the end, the information we're interested in, or the resources that we're interested in, or the hazard information that we're interested in, whatever it is back in the rocks, right? So fundamentally, the models should serve the purpose of allowing us to better understand what the rocks tell us and you know, decode that information. So I don't think we should lose sight of that. And I think there is a risk with the modeling, and I would definitely fall into this category, that you can come up with all sorts of clever ways of analyzing the full information that you have in a model, but it's then very difficult to apply those same methods to analyzing much less complete, sparse data that you get from, I mean, particularly from outcrop. So somehow we have to kind of bridge that gap as well. We have to take advantage of what we can do with the more complete data sets and the more complete models in a way that we can then still, you know, use some of that at least to get more information out of the more limited data that we have as well.
Yeah, I think the points y'all both made are exactly right. I think it's one of those, you know, we've all kind of, you know, when staring at an outcrop, right, we interpret with certain biases that are based on outcrops we've seen before, or limited well data sets or seismic data sets that we've seen. And I think, you know, the point you made is right. These forward stratigraphic models are there to kind of serve the model, or the outcrops, and help us interpret them better. But you know, I've definitely, you know, I've spent years of my life staring at outcrops and then looked at a forward stratigraphic model, only to realize that one of those quirks in that outcrop that I never understood what that could be, could potentially be, you know, a strange perspective on a feature that makes perfect sense when you look at it from the flow process standpoint. So I think there is an opportunity to, you know, the depositional models and the classifications that have been built, they were built on a lot of observations, and I think we can refine and make them, you know, for example, a little bit more three-dimensionally or process conscious. And what's kind of interesting is when we look at the models, you know, individual labels might change. Some of the fundamental observations that have been, made across outcrops and data sets are some are consistent and some have to be updated with new things. So I think it's an incredibly exciting avenue to actually look into. And I think, you know, whether it's the forward strat models or even just monitoring all the monitoring, you know, where plastics are going, for example, I think, you know, you're Florian, your point that you're making about plastic, you know, markers, I think is pretty amazing. I wonder if we're actually going to get new rates of how potentially things like contorites drift. Do they drift at completely different rates if we have increasing high resolution of being able to detect differences in plastics and what years they came out? Well, that was pretty amazing. So there's too much exciting stuff to look into. So here's a question right here from David Gamboa. Maybe an aspect that could be relevant is the scale. Outcrops may not cover the full scale at which hydrate systems are seen on seismic. And yeah, I think that's a point that, you know, Alexei and Jess, y'all could speak to as well.
Yeah, I guess something that's always tricky when you're looking at outcrops versus seismic. So around New Zealand, for example, we've been looking at paleo seep sites, which are onshore. But obviously you're seeing something at scale there, which you'd never actually be able to see in seismic. And so trying to relate the two together can be, obviously has challenges. So yeah, bearing that in mind when you're looking for paleo examples as well is obviously very relevant.
Well, I'll just add that it also depends on the frequency of the seismic data, right? So we can see pretty slim seismic chimneys if we're using some chirp data, for example. It depends on how you define seismic.
It's kind of, you know, this might be, you know, a question. It's kind of random question, might be simplistic, but when it comes to the hydrates, right? They don't, obviously they crystallize, right? Is it kind of in situ crystallization up front and kind of growing, or is there actually some migration of the actual kind of gas in the first place prior to the actual crystallization?
It depends, basically. So you can have, there's lots of different ways that hydrate can form. You can have it forming in the interstitial spaces between sediments, as really granular, or it can actually form lenses, in which case you will get, it essentially will kind of fracture and force sediment apart. So there's lots of different kind of morphologies you can get hydrate in, and that will depend on the exact conditions under which it's forming.
Okay. So I guess would there be something like an interaction between the processes under which it's forming and maybe the actual character of the deposit it's forming in, you know, like the heterogeneities, for example, some of those channels you were looking at, Alexei, versus the levees, depending on, you know, it's interesting to kind of think about, you know, whether it's hydrates or, as we'll kind of talk in the next series of sessions, you know, the heterogeneity, the internal complexity of these deposits that, you know, everyone in this community has been kind of looking at for a while are are just as relevant potentially from the hydrate perspective, from the carbon injection and sequestration perspective, and even just, you know, trying to understand where things are going. So I think it's exciting to see some of the concepts that have been had actually get even, you know, renewed interest because of because of new energy resources, and well, now we need to store carbon.
Yeah, you're right, Fabien. Here at UT, we're trying to grow hydrates in different types of sediments. We have a lab here, and so we study. It's the more we do it, the more complex it gets. It's just like, you see, like what we're calling the coarse grain sediments is actually, like, I've just rechecked the numbers from this site GC955 that just definitely knows very well. It's one of the like natural labs where we've been drilling hydrate for like about 3 years ago. So we find hydrates there is what we call sandy sills, and the grain size there is about 10 to 100 nanometers, and it's a very fine boundary between like a clay sill and sandy sill there, right? So, and still, like when we retrieve this sediment cores under pressure and then we depressurize them, it's a very, very fine grain sediment. So, and it depends very much on where you grow this hydrate. If you're growing it in coarser grain sand or in these finer sediments, And hydrate can grow in different manners and fashions, starting from the grains toward the centers of the pores, from the centers of the pores towards the grains. It depends on how much methane you have, on the concentration of hydrate, initial and final. So it's a very complex process.
Yeah, it's really complicated, and then basically you can start modeling it. You can obviously do the practical experiments like Alexia was saying. We've been doing it from kind of like the modeling aspect, I guess, and to get down to that level of detail in the modeling just becomes impossible at kind of basin scale. And so it's a very, it depends on what kind of size you're trying to look at. So yeah, there's just too many factors basically.
Okay, so kind of building on the theme of modeling, right? This is again from David Gamboa. Modeling capacities have been greatly advanced in the application of, to lobes, turbidites, and that's kind of understandable. How applicable can some of these new methodologies to model different types of submarine landslides, and importantly, some of their internal complexity? Guessing that's more of a question for you, Alexander, if you're on.
Yeah, I'm here. I can't really answer to the modeling capacities, how that can be done. However, I can say that for the monitoring, a lot of effort right now is mostly focused on understanding timing of events and the triggers of the events, mostly because that's what's easier to do, even though it's quite hard to do. But then getting into the landslide deposit architecture, of course, and how the landslide evolves downslope, and that becomes much more complicated from a monitoring perspective. So modeling can be really interesting. So I'd like to hear maybe others on the modeling perspective for the submarine landslides rather than turbidites.
I think kind of one of the questions I was gonna ask when you were showing some of your work is, have there been further repeat surveys where you didn't detect landslides, but you detected either additional erosion or additional deposition downslope from some of those, maybe kind of highlighting that, those evacuation scarps then are avenues that sediment gravity flows can, things coming off the shelf can capitalize on and actually start flowing down. So actually visualizing or seeing that headward, the development of potential canyons or gullies through that headward erosion.
So, well, we can do that, not specifically in this study, but there's been other studies that have looked at that, mostly in Monterey Canyon. It's probably the best example where they've been able to do some repeat mapping along the canyon thalweg, but also having some ADCPs along the thalweg and trying to see the evolution of turbidity currents going down. In our case, we've been able to see other landslides being formed and in that same repeat survey. And we're not sure exactly what triggered those ones, although we do think that some of them might be also triggered by iceberg just impacting the slope as they're moving in and out. So I'd say, yeah, it is possible to see kind of superficially what's happening in terms of the evolution of submarine turbidity currents and submarine landslides. But then to the specific question of looking at the deposit itself, I suspect that's much harder. And maybe that's where maybe that's where the question about the modeling capacities, which has focused more on turbidity currents, maybe that can be applied to submarine landslides.
Excellent. Another question about hydrates. At which burial depth can gas hydrates still be found? This is almost like a limit on. I guess I wonder if that ties to that gas hydrate stability zone.
Yeah, there's a simple answer to that. So it depends on the water depth and geothermal gradient a lot. And if to answer that briefly, you can find them in the water depth starting from like 350 to 400 meters water depths and deeper down to up to 1 kilometer below the sea floor. It's like averagely on Earth. Normally in the Gulf, we find them between 300 meters and 900 meters.
Yeah, so around New Zealand, it's below 500 roughly, but around places like Antarctica and the Arctic, you'll find them potentially shallower because you've got lower geothermal gradients and colder temperatures. So it's just a fresh temperature condition.
Fabien,
Yes.
I think we have to wrap it up, even though, and I would like that we continue discussing. It has been a very exciting afternoon for you. In my case, it's getting dark. And I have to say that this is going to, you know, it was great to hear that people would like to continue. So we for sure are going to organize second part in the sprint. We are going to try to take some of the topics that we touched today, but also we are going to include other topics that we were not able to have more speakers coming in today. I have to say that I appreciate everybody who has do their presentations. Sadly, Florian has to leave a few minutes ago, and I don't know if Celeste is around and she can turn on her camera. I have been trying to see if she is able to do it. I want to, for the people who are still around, if you are interested in participating in our special issue with the TS, with the sedimentary record, it will be a great opportunity for you to show some of the stuff, new stuff that you are coming in. One of the beauties in a sedimentary record is that they also have an area where you can actually show preliminary results. So that is another thing that is, I would say that you should think about it. For the people who are still with us, I would have to say that I appreciate that you have been giving us so many good discussions. We will for sure start organizing this for the next spring. So thank you very much. And I'm not sure if we can do one of those panels. Cassie, I don't know, have you ever done so one of those panel photos in this format?
Do a screenshot of everybody's face here together. I don't think
yes,
a little
but you know, one of them, I have seen one of them, and it's kind of like right now everything is in one line, but well.
So I can do one of those. And again, just, you know, for everybody heading out or whatnot, thanks for taking the time to listen in. Again, Lilian did a huge amount of work to get this set up. So Lilian, thanks for that. Emma as well. She couldn't be here today, but there's a massive amount of work there. Jen and Cassie, thank you all for the support. And the presenters, I think the presentations were so interesting, and I think hit directly at what we were trying to showcase with this series of talks, that the amount of work that, or the amount of interesting topics that are there, there's a huge amount of topics, there's a lot of interest, and there's some pretty unique opportunities that are there. And I think you guys have demonstrated to everybody attending the excitement around the topics that you guys are working on, and kind of where there's some more opportunities for other people kind of that might question, you know, well, okay, I'm going to kind of pivot away from one thing or another. There's a huge amount of work that can be done in Deepwater Sed Strat still. So thank you guys for taking time to do that.
So the future looks bright.
Yes.
Especially for a lot of students who are interested in, you know, and they maybe would like each one of these areas is still a lot to do. So it's fantastic.
Absolutely. All right. Well, if you want, Lilian, I can take one of those screenshots, and I'll give us a 3-second count, and we can take that. Okay. All right. 1, 2, 3. All right. It said it was saved to my desktop. I will check that. Again, do not hesitate, the presenters and others, to reach out to us, submit abstracts or ideas for those special publication topics. So again, thanks to everyone. We will let everyone go, and have a great rest of the evening and afternoon.
Thank you, guys.
Bye.
Okay, thank you.
Thanks, folks. Bye.
Thanks, everyone.